You the link. Okay, we're ready when you are.
Okay, I can't sign in. I don't know why. Niall, do you want to try signing in? Sure. I don't know why mine.
And this is the Lunar Supply Pod team.
No, this is the robotics.
Oh, this is the jumping robot. And you have three of those teams.
I'm in my
Yes.
I'm in my email.
Oh, you have to open up the PowerPoint, right?
Yeah, where is it? It's in.
Just go to Google.
Did you share it with me?
Hmm?
Did you share it with
Yeah,
me?
you go for it. You go for it.
Did you share it with me? No. Okay, can you get it on there then?
No.
Hi, sorry, trying to.
That's okay.
No, you're fine.
Trying to join from the Zoom. I can't join on my main computer, so I hope this will suffice. But where should we start? You want to see our CAD or our physical prototype or?
Well, why don't you start with your physical prototype and we'll see what we can do. How's that?
Sounds good. I'm Niall Fox.
I'm Gracie, and we have a third team member who's
He's just not here. I think he
now.
forgot that second period he's supposed to come here instead. But this is our physical prototype. As you know, we're the jumping robot, and
Okay.
we wanted a really unique way to challenge this or to attack this challenge. So we looked online, we looked at a lot of different. Oh, first of all, we're the propulsion sub team. So we're the
Okay.
sub team meant to deal with getting the robot in the air. That's basically it. That's all our job. And so we decided that we wanted to have a really unique approach. So we wanted the body of the robot to be part of the jumping mechanism. And we watched a lot of YouTube, did a lot of research, talked to people on forums, and lots of people liked the Do you know Veritasium? They're like a
Yeah.
science YouTube channel.
Oh yeah, I love
They're-
Veritasium.
Yeah, they're really smart. Their videos are amazing. But they showed off a design. There was the body of the robot being like
Right?
springs itself in a sense, because these are right now pieces of acrylic that we cut on a bandsaw, and then we
Okay.
connect them to this 3D printed little I don't know. This was meant for our robotics team. This is like a hub adapter for hub shafts.
Yeah, I think
And
that's smart.
we just attached it to the top of this, and we have 4 right now.
Uh-huh.
And if I could show you how it jumps, I
Yeah,
can.
let's see it.
Let's see. Let's move this back a little bit. So
What kind of height do you guys get out of this thing?
we have our furthest right now is about 1 meter. So right now we compress the thing all the way down by touching the 2 hemispheres together, and then we pull it to the side, and it jumps pretty high.
That's terrific.
Yeah, and we
And that's
basically
acrylic.
huh?
And that's acrylic.
Yeah, it's I don't know exactly what type. Do you know what exactly type of acrylic this is? Or it's just normal.
It's 2-layer acrylic.
2-layer acrylic.
Very
And
good.
we just decided to get the most bendy kind of elastic material that we had in the shop that we could just cut and put on something really fast. And this is almost exactly what the Veritasium video had. They had little sides that could bend and store energy.
Sure.
And our plan is to have a motor of some sort, probably a brushed DC motor,
Uh-huh.
connected to a pulley that has a string wound to it. Then the string will run from this side to this side and be knotted on the end here. And
Very
so when the motor runs, it'll make the string shorter, which will pull the 2 sides together like such.
Terrific.
So it runs and it'll pull like that. And so we just wanted a really easy way with one motor to jump. And we looked at a lot of other designs. There were some that kind of bent like a knee and then jumped, and those weren't getting quite the height that we wanted. And
Sure.
we decided that this would be a really good idea because it's really weight efficient. You don't have to have lots of heavy springs, and you can be really precise on what material you choose for these.
Okay. Very good.
Yeah, and
Okay.
also it's very simple.
So one of your next steps is to be working on the mechanism for pulling it tight, right?
Mhm.
Okay. How do you see doing that? What's your plan?
Right now, here, do you want to show them the CAD? We
I
have
think it's not that
our CAD pulled up. You can
I'm
see.
not sure if this can.
Yeah, I can see
You
that.
see it?
So this is the top part, and there's going to be a bracket that a motor can mount to. We're going to put it on the outside and have the string just run uninterrupted down and have the
Okay.
weight of the motor at the top so that it balances easier. Like if we had the weight down here, it'd be harder for it to jump because this side is getting sprung upwards. And if we
Right.
keep it on the top, it'll like pull itself upwards.
I think you're right. Okay. And so then the question becomes, so you've pulled it tight together. So you've compressed your spring, so to say. Now, how do I release it quickly?
So this is what Aiden was working on a lot. He has a lot of background with like cars and stuff, and he said maybe a dog clutch, if you're aware, like two sides of a clutch, they come together, and when they're engaged, they have teeth that make them rotate as one, and then when they're pulled apart, one of them can rotate freely while the other one cannot. And so we
Okay.
were probably going to attach the string on the side that can rotate freely, maybe on a bearing or some sort, and
Okay.
some sort of actuator, maybe a servo or something that can pull the two apart and push them together again.
There you
So
go.
when we want to release it, we'll just pull them apart, and then or not the string can wind whichever way and then jump.
And I like that idea. I'm wondering, and I hadn't thought of this before. So what if you have if there's a shape on the very bottom of the string, so that as it winds up, the shape on the spring is what activates the release.
I haven't thought about that. That might be,
That's new for me as well, because I wasn't thinking of, what did you call it, a dog clutch?
yeah, a dog clutch. Some sort of dog clutch. Maybe not exactly what is used in cars. A modified version that we could CAD in-house.
Sure, and I think that you can do that. It implies that there's, so if you've got these two pieces together, there's some kind of a spring force that's pushing them together,
Mhm.
right?
Yeah.
And then if you have like a shape on the string that's kind of wedge shaped, it would push them apart long enough to
Oh,
release.
I see. So then when it gets down and contacts that shape, it will just automatically split?
Right. Now the trick is, as soon as it comes up, it will release, but as soon as it starts releasing, it'll come back together.
Mhm.
So there has to be some kind of mechanism. So I I applaud you. I think that his suggestion sounds like a good one. I'm not familiar with that dog clutch, but it sounds like a great idea that I think you can work with.
We
Okay.
have the basics of that clutch.
Yeah.
Here, these are just the two sides, and they have teeth that can mesh together.
Yep.
And we'll probably have a pulley on this side
Sure.
that can then rotate without back pressure from the motor.
Yep.
Because if you were to just have it still connected to one pulley, that when you wanted to reverse it, if you didn't have power on the motor, the fastest that the string could go back to its fully extended shape would be the fastest that you could apply back pressure on the motor and run the
agree.
motor backwards. So we wanted to use a DC brushless motor or brushed motor for the winding of the string. So it
Yeah.
has enough torque to actually wind the string. And in space, I don't know if strings would be the best thing. I don't know if like a rope as in like, the
Well, don't
rope.
worry about that just yet.
Mhm.
However, so if you use a monofilament, like what they use for most fish, don't want stretchy. But if you go for, you can get like either a braided or a stranded fishing line. They're a lot less stretchy, right? And that might work better for you. Okay.
Yeah. We were thinking, are you familiar with like Dyneema rope?
No, tell me about it.
Dyneema rope is just like a thick winded cord. It's like a cord. It's almost, some of them are made of Kevlar or Kevlar inserts and stuff like that, but their applications are usually for like robotics for elevators, for running strings for pulleys for elevators. And I've had some experience with Dyneema rope on FRC, if you guys know FRC.
Yep.
Robotics competition. I'm on a
Yeah.
FRC team that use Dyneema ropes 2 years ago to make our elevator, and
Sure.
they're very strong, but they're also they act like a normal string. So
Right.
that was
And
also
that sounds good as long as you can get something that's thin enough because you know, you're really trying to keep your weight down any place that you can. Okay. No, I like the idea. Good job, team.
Thank you. And that's basically it for the propulsion side so far. We do plan to add 4 more of these because
Uh-huh.
larger the number of the things or the springs, the more it can
Sure.
jump, more force it can store. We don't know our ideal thickness of these, but we're trying to get 8 of them all the way around. So
Okay.
it'll be symmetrical anywhere you put it.
Okay. And as a thought, it looks like you've got it so that the screw goes in from the inside and then you have extra on the out. You might want to just reverse those. That way you have a little bit less sticky poking out on the ground there. Does that make sense?
Yeah, I see. One thing that we were thinking about is possibly like regolith from the moon. It's pretty sharp. So if we had our robot land like this, it might splash it up and then could possibly cut our rope. So we might have to run some sort of like compressible, like plastic shielding around the rope maybe to protect it from being cut.
No,
Or
that's not a bad idea. I mean, even if you use braided, right, you could put some kind of a coating on the outside of that braided filament, and that would prevent dust from getting inside of it. But that's some really good insight, good thinking. Um, oh, now here's another thought. Um, I see that you want to bring it all the way down. However, that puts your weight all way up high, and that might make it difficult for it to be turned so that it's on the flat.
Mhm.
Have you thought about can you put it in the middle a little bit? So you've got the ball size. Can you put it so that so that some or part of your package is inside?
We could totally figure that out. Our CAD is very robust. Like it's very easy to make changes to, and our lead cadder, Aiden, is very skilled. So he could find some way to put the motor or weight in any orientation or any spot. We just have to do some testing and figure out
Can I
where
jump in
that's
for a
best.
second?
Yeah.
Okay, so like
Sounds
with
good.
like ideally with this, we're not gonna
Evan,
like,
you're not-
huh?
Oh,
Evan.
come over on this side. There you go.
All right, yeah.
Yeah, go ahead.
Or whatever. All right. So ideally in our final version, we're obviously not going to be using 2-layer vinyl in our final one because that doesn't work on the moon. It just like melts or freeze or whatever. And so I was actually looking into this recently, but like probably as our final like material choice for this, it's not going to be this flexible because it's hard to find something with such a high elastic limit that can actually go back and not deform when we do compress it down this low and the problem is we still want to get energy out of it and still make it compress. And so I was looking into like I think it was polymer matrix composites, just like polymer composites. I found like also some metal matrix composites,
Sure.
but how they work, do you know, have you heard of those? I assume
Sure.
you've- but like when they're like I think it's when they're sewn along like the same line, they're bendy in that direction. So I was thinking of using like something that isn't as I don't know if I can find that something that's as elastic as this is, and that was like our next best option. But like in regards to how far we're bending it down, I think that like we wouldn't be able to bend it this far down anyway because we wouldn't want it deforming or cracking on the moon in those temperatures or whatever.
Sure. Well, and you might take a look at polycarbonate.
Polycarbonate.
And you can get that at a hardware store. It's also called
Lexon?
yeah, Lexan. That's right. And then you might also you can look at fiberglass, and you can also look at carbon fiber, right? Each of those has some different capabilities that make
Mhm.
those are I like where you're going with these kind of things. I think that they're along with your suggestion. I think there's several things that you can play with and see what works for your budget as well as
Yeah.
for the experiment itself. Okay. Good job, guys. I like it.
I would like to say about material, every different material that we would choose has a different spring constant, right?
That's right.
So the optimal position for the winding or like how far we would go down could be different for different materials, and that would
You're
require
exactly right.
and the bending of these is not past the point where it starts not giving as much energy. So
Yeah.
all the way down on this is the most energy we could get. But if we went further, it might give less or more. Who knows? But with different materials, we'd have to find the sweet spot. Which
I
one?
agree. Now, and then you probably noticed that on the other one, on the one that you saw in the video, they also had some extra rubber bands that they put in there for some extra force. And obviously, rubber bands are not going to work in space just because they'd either heat up or crack or whatever. But I mean, if you looked at springs, what type of springs might work for that same kind of extension or capability?
There's lots of constant force springs that are like they're flat pieces of metal that are wound on top of like it's in a circular shape.
Yeah,
That
you're right.
might work for that because if you have the circular part on the string, it could get longer or it could get shorter depending on how far away this is. And when we compress it, these two sides here and here get further from each other, and that spring would get longer. And then when it gets back, it'll pull itself back up. So that's a
You're
very
right.
I was.
Okay.
We do have Zach. Do you want to talk about the reaction wheels? Because we have to find.
You guys want to talk for a bit? We have like.
Okay.
I'd like to start talking about all the stuff we've been doing.
All right,
Cool.
uh,
Do you want to
Can
come here?
mute Woodbridges?
Yeah, yeah.
This room?
I just want to mention that you said you said it jumps a meter. So really anything 3 feet, between 3 feet and 10 feet is perfect.
Sounds. Thank you.
Ideally, we want it to jump higher.
We want it
but-
to jump a little higher because we could always change the jump height code based on how far we're compressing the springs. So we want to know our maximum with 8 springs.
Not necessarily.
Not necessarily.
We might not be able to change the height if we use some.
Well, you guys have a high roof there, but most schools, if they jump 10 feet, they're going to hit the ceiling. So
Oh, yeah.
We don't know
Okay.
what height we're going to aim for, but probably more than what we have now. Always aim higher than what you.
That sounds great.
And then
Well,
we're hand it over
and
to
as soon as you start adding any materials in there, you're going to have more weight,
wait.
and so it's going to make it more difficult. So that's okay. Just keep that in mind. Of your biggest deal is how do I keep it so that it's not heavy? Okay.
What weight would be considered like the upper limit of what we should aim for, or what range of weight should we be in?
You're probably wanting to be under a pound, right? And also think about it in terms of if something is dropping, 10 feet, what's okay to hit your foot, right? So trying to minimize damage to people is one of my goals there.
Yeah. Okay, Zach,
All right,
gonna
we're gonna-
talk about.
Yeah, can you mute
We're-
Woodbridge?
Yeah, we're gonna mute on here and then he'll talk on there. Thank you guys.
Sounds great. Thank you.
Thank you. Good job.
Bye.
Bye-bye.
Here, I'll change hats. Okay.
Yeah, I'm actually
Here,
showing.
wait, just bring it.
This
Wait,
works?
pull it up.
Yeah.
Wait here, hold on. Can you send the email to talk for a second without it, and then can you send the slideshow to
No, it's not.
He can drive it on that one and share, and then talk from yours, right?
Oh, that's what it is. I see. That's very cool.
Oh, yeah, okay.
Hey, you should just come over here and explain.
Yeah,
it,
yeah,
'cause
yeah.
I think.
So, yeah. So I have this
Wait,
camera.
Possibly, we just bring all of this over here, and that way I can see.
logistical issues.
Yeah, sorry.
Okay. So, does it see the live stream? Yeah. So, do you see the Zach Hagelberg and how it's got like?
Yeah. Oh, okay. Hold on. Let me.
Pin it.
So I can add a pin to that one. All right, I can see that.
So I have this microcontroller right here,
Yeah.
and yeah, it is currently we got it this like small camera. Well, it's we have a small camera on it.
Okay. Very
Yeah,
good.
and
So
we
you
got
have
a
you
bunch
have
of
a
code.
and what's your camera hooked up to?
The camera is connected to something called a Seed Studio ESP32,
Okay.
which
And
allows
so do you have it
has
hooked up to like a Arduino or a Raspberry
it's
Pi or
really
what are you
this
doing
thing
for?
right here is a really small microcontroller.
Okay, very
It's
good.
very small weight. It has a antenna built in.
Very good.
That camera I showed you that's
Uh-huh.
currently live streaming. And it also has a bunch of pins on the back. Of
Very good.
I've connected three wires. Uh,
Okay. So it sounds like you've got a good beginning for your camera and potentially your control thing. Is that right?
yeah,
Control computer?
we might want a higher quality camera in the end because like that's the entire point we're going to the moon.
Sure, but it's not the critical thing at the moment. The fact that you've got a camera and it's functional, that's great.
And the other thing we're working on, if you can see,
I see you've got a motor.
I have a motor. Uh,
Very good.
it's a brushless DC motor,
Sounds
and
good.
the three wires right here.
Uh-huh.
It's connected. Oh, that's three wires connected to electronic speed controller,
Okay.
and then
And you can control
these
the speed on that?
we can't yet. It's
Okay.
not code, but here's a battery that's connected to the ESC,
Very good.
and these three wires. Two of which connected power and the 5 volt power and ground of the of our microcontroller, and one control connects to an analog pin.
Excellent.
So we're
Now,
hoping to get the code so this actually runs soon.
so it sounds to me like you guys have most of the components you need here, right?
Yeah.
So when your camera is transmitting, are you able to pick it up on a compute? Is it picking up on your computer or is it on your cell phone or what's it on?
It can go to any computer with the Wi-Fi, I think.
Oh, okay.
We happen to have it on the same computer that's connected with USB to the microcontroller,
Okay.
but we can also pull it up on any other computer.
Okay. Now, can that microcontroller work autonomously from your computer, or is that what's driving it at the moment?
Right now, it's connected with the USB to the computer, and I think we needed that so that's powered, I think.
Okay.
It might be possible to connect this to a battery and run it autonomously, but we haven't done that yet.
Sure. And that makes sense too. So I think that's exciting. It looks like you're on a very good path. Um, and then, and so have you started working out the code for how you want to run that motor?
No, we've seen how, but
Yeah, like we have ideas for like on the same screen where we have our camera, we want to be able to control the robot from there, so it's all in one place and easy to use. So we're gonna try to figure that out sometime soon.
and then we also have some plans for what we're using for the motor. Do you want to talk about
Yeah,
that?
okay. So for our motor, we had like a couple options. Like this one
We're
here
using
is like
brushless.
brushless, yeah, because it has a lot of power, so then we can so for
This one,
example, our reaction wheel, so then we can turn easier.
1,100 kV.
Yeah.
So how many motors are we going to use in
We're
total?
using in total 3 motors, like wait, 3, right? 3 minimum.
Yep, three.
And then
minimum.
2 for the reaction wheels, and then 1 for the actual propulsion. It's kind of hard because we have our speed controllers, but they only work with like either brushed or brushless motors. So we don't know. We have to make a decision between those two.
Yeah.
Okay.
So
That sounds really cool. Now you may want some gearing to go from your motor to that to your spool. So the next question is you've wound up the string. Oh, we were just talking about that. So you guys are okay.
That'll be handled mechanically.
Yes, I think so. You're all about the controls, so I think that's great. Now, so is this going to be a continuous video or is it going to take still shots?
It's gonna be a continuous video with that set up right now.
And that's fine. Where do you think it's going? Where do you think your camera is going to be placed? How are you going to get the pictures that you want?
I think we want to put it on the top because anywhere else is slightly.
No, just probably the
sideways.
side of the robot.
Oh, sorry.
Yeah, so these motors, two of them are going to be used for reaction wheels, which will allow our robot to control itself without touching the ground.
Okay.
Thinking like pitching over maybe just a tiny bit, so we get the propulsion mechanism out of the way and we can take clearer pictures.
Okay.
So our camera will be on like the side of our robot.
Okay. Is that going to make it tilt over by having extra mass on one side?
We're going to make it tilt over by spinning the reaction wheels.
Okay. And that's all right. Well, okay, so each one of them would have to have its own motor. That could add quite a bit of weight, couldn't it?
Yeah, we're only gonna have two there's three axes, but we're actually thinking about only having two reaction wheels and using two axis control.
I'm okay with that. So with those, you might want although you want some pretty high speed out of those, you might also want the motors to be fairly small, right? And so just look into that. I think that's exciting. I like what you guys are doing.
The specifications we want, yeah.
Oh, now what are you guys thinking about for solar panels?
We don't really have a team working on that very much.
Okay. Well, and it's part of the power, right?
Yeah.
And so take a look at what kind of things are available. Now, this thing is jumping on the South Pole. How does that affect the positioning of your solar panels?
They would be on the side, right?
Very good. It's not going to be on the top. You'll want to put it on the sides.
Like 1 point something degrees inclination, so that's
Something like that. Okay. Very good. It sounds to me like you're already on it. So that's good.
Yeah, we haven't got the specifications for what solar panels
I
we
was
want yet.
looking at different types of solar panels, and I was thinking maybe really thin solar panels that maybe are just flexible, and then you could line the outsides of these, which are the only faces that are actually on the outside of the robot, and you could line the sides with solar panels if they make solar panels that can flex. I don't know if
They do. They make some that will flex, but of course they produce less power than the ones that are non-flexible. And so these are perfectly good options for you to consider. I mean, depending on how flexible they are, could you have a strip by having two strips where they're facing outward, right? So I've got solar panel on this side and I have solar panel on that side. You might be able to work it so that you're getting power out of double the amount. And then you're also depending on it to be the flexible material, your spring material. Just an option, right? I don't know that you'd be able to get that much double duty out of them, but it's worth exploring.
One of the reasons that we're having like a second reaction wheel is being able to like roll our robot. I'm not sure if it's roll or yaw. Roll.
Right. So if it's jumping like this, and you think that you want to make it rotate a little bit while it's taking pictures,
I would say maybe that's roll. That an advantage of adding that reaction wheel is we could have all of our solar panels always facing the sun.
very good. I think that could work.
Your cat. There's my jokes to talk.
Okay.
that's pretty much it.
Okay. I didn't ask about your battery. Your battery looks fairly small. I think that's really wise. What kind of weight do you have on that thing?
I don't know.
Not sure. It's
11.1 volts and 450 milliamp hours right now.
Okay, very good. It looks pretty small, so I think that that's a great step in the right direction. Okay. Any other questions?
Do you want to talk more about body or?
The body is the purple.
Oh, yeah,
So
yeah.
I don't
Okay.
know. Material, that's about it.
Well, okay, now wait a minute. There is more to the body than just just the rings that you've got.
Yeah.
I mean, for example, the box that you're going to use to contain your motor and your electronics.
Yeah, totally.
Like wire management and
Yeah,
stuff?
all that stuff. So like right now we just have this, and this might not like we're pretty sure this is gonna be our final design, and I'm working on that right now. But like this, I don't want to get like too ahead of myself with designing a bunch of stuff and then like not using it because and also like with our design, most of the actual like propulsion system is gonna be the structure. But and so I'm just working on like making something that can actually hold all this stuff and how we're gonna attach all of it. That's what I'm working on.
I think that's a great idea. That's fine. And you might want to space those out a little bit. So right now you've got them where they're really close, but as you go to 8 pieces, spreading them out a little bit might give you a little bit more room for other things to do. So I like where you're going. Keep this up.
If when we use reaction wheels to spin the robot or roll it or pitch it or whatnot, the wires could tangle with each other. Maybe not if the whole thing is moving at once, but if they do happen to get caught on each other, it'd be pretty bad. So good wire management and maybe really lightweight slip rings
Yeah.
around
Eh,
points the wires contact parts of the body so that the wires
Sure.
don't snap on each other.
Yeah. And um, I haven't worked with reaction wheels for anything like this before, so that's something where you're gonna have to play with it a little bit. I don't have any good suggestions for you on that. But no, I think that it's possible. Um, and one of the tricky things is that by having reaction wheels, you want them to have some mass to them so that they're doing something. But in this particular case, it's also going to be you're fighting with the weight of the robot altogether. So there may be some difficulties with having reaction wheels on this particular problem. Does that make sense?
One idea I had is not doing a wheel structure, but maybe like a different structure. Because the main advantage of wheels is that wheels don't have like don't have drag when they spin, but that's not a problem on the moon, so maybe we can change it to something like a hollow structure.
Okay. Yeah, I can see that.
Or
Moving
even
all
if
the weight in the middle,
if the
not doing as much.
even if the motor spins fast enough, you wouldn't necessarily need a full wheel. You could have just a line, right? And then that would also generate a torque, would it?
Yeah.
So maybe
I'm not sure. I didn't quite follow that. What do you mean?
so you could have a wheel on a motor, or you could have just
A bar.
a bar or like a diameter of that wheel on a motor to reduce how much.
Okay.
I don't know if that would produce the same torque, less or more.
It's always the same torque.
Always the same. So maybe
Yeah.
not for at least on the moon
The speed.
because of that.
Yeah. No, I'll let you guys explore that a little bit. Okay. Very good, team.
Do you think that brushless motors is the best choice?
I think so. I mean, especially in a dusty environment, I think that that's a wise choice.
Already.
Yeah, really good. I like how you're proceeding on that, and I like that you used the acrylic right in the shop. It's flexible, it does the job.
Yeah, it's a good
So-
starting.
So did we listen to all three of your teams?
Mhm.
Yep.
Okay,
Excellent.
good. Okay, because it's 10:30 your time, and you still have your Lunar Supply Pod team there, or don't you? Okay, so I have to ask Bozeman, Carl, if you have time to wait. They have one more team presenting the Lunar Supply Pod before you, because we're behind in schedule.
Okay, so don't send them out yet, or
Let's see what Carl says. How long are you guys in your class? Are you in it?
it's this period for like
5 more minutes.
5 more minutes, and
10
then we have homeroom. So that we have wiggle room. Yeah.
You have wiggle room? Okay.
Homeroom is
So
30 minutes and then
let's see. If Carl, do your kids have wiggle room or should they
We
present
have
now?
class until 12:20, so another hour.
12:20. Yeah, so you have wiggle room. So is that all right, Carl? If they present their lunar supply pod.
I mean, I think they have, oh, another presentation. Yeah, that's fine.
Yeah.
Oh,
Okay.
yeah.
Okay. Bring
We'll be
bring
back.
in your lunar supply pod.
that's good.
Oh,
There shouldn't be this time for us.
Do we need to get our stuff off the table? Yeah. So is this Zach's computer?
Yeah, this
Do
is
you want me to take this to him? Okay.
Zach.
We gotta get our stuff. And we should leave the meeting on our computers that isn't this one. Our supply team, lunar supply team is coming out. right now.
Okay. Thank you so much.
Bye guys. Thank you for the insight.
Thank you. Have a good afternoon there.
Well,
Nice job. Impressive. Yes. Hello, supply pod
Hello.
team.
You can see us fine?
Yep, and we hear you fine.
Awesome.
So introduce yourselves and tell us what grade you're in
So you guys-
what's your future after high school.
Okay. Well, I'm Cruz. I'm a junior, and my future plan for after high school is to probably join the Air Force and be a load master, and then after that, most likely just joining the fire service.
Awesome.
That's cool.
Yeah.
Alex?
My name is Alex. You may recognize me from the NASA Hera group. And
Uh-huh.
my plans for after high school is probably work at Boeing while going for a 2-year degree at Bates Technical College in Tacoma.
Oh, wow. Awesome. Yeah. The Hera group on the Moon and Marsscape robots. Oh, and there's one more member.
Hey, hey.
I'm a sophomore. And after high school, I'm planning on to go into bioengineering, so medical field.
Oh, awesome.
Can you say your name again? I missed that.
Elizabeth.
Elizabeth. Excellent. Thank you for saying that.
Okay. So you could share your screen or
Yeah, tempting.
yep, it's coming in.
You got it? Okay. Alex, you got control of the thing?
Yep.
So we're the supply group pod garage and airlock group. Our ideas are to follow the mission objectives of like keeping it all like keeping a safe structure for the storage of the supply pods, and just to keep our astronauts semi-protected from the elements of radiation and the sun and stuff while they're working on getting their stuff from inside the pods to the airlock and inside of their station.
So mission objective, basically design a lunar airlock big enough for what, yeah. So I'll go over the problem here. Right now, the main issue is that the space suits that the astronauts are using are too big and bulky to be able to go in and out of the supply pods, and the filtration system isn't as good. So those are some of the issues that we'll be covering today.
Oh well, our design is to have it be a semi-rigid dome structure. We're planning on using the what is that? I can't read that. The name of that.
The Vectran.
The Vectran folded around like a titanium frame, like custom sewed to fit around like a titanium like triangle frame to just protect to just like insulate our astronauts from the radiation so they can use more thinner and like more what's the word? Lightweight and movable or what's it?
Transportable.
Transportable like spacesuits that just protects them from the lack of oxygen in the moon's atmosphere.
Okay, hold on. Let me pin that. I want to see your. Okay. Okay, so right now, is that like what is that? Like a buckyball? Is that what you're looking at?
It's just like it's a dome base. It's just to like give us an idea of like what it would look like in a physical 3D space because modeling it in like a CAD program is a lot more complicated than it is to just build like just a little quick prototype.
I agree with you completely. I really like building it more than I like drawing it sometimes. Okay, so is your intention that it's going to be a lot of triangles like this, or is it going to be all flexible material? What are you guys thinking?
All the triangles are going to be more solid. It's just going to be like a triangle frame with a flexible Vectran fabric like built sewed so the frame's on the inside of it.
Yeah.
Going to have it be like we've been looking at like origami and stuff like that to like give us an idea on how to make it like easily assemblable for the astronauts.
Okay. And um so that means if there's some rigid structure, you've got to have places for it to fold. And that makes sense that it would be on the edges of your triangles. And so do you have to have some space in between so that they can fold together for the shipment? How do you think you want to do that?
That's one of the problems we're running into right now is like coming up with a way to have it fold around. We're thinking about maybe using like having some like extra bits. So like we have like we're thinking about using like zippers and stuff to like create like the foldable parts. So it's like easier in storage. So then we can like lay it all out, zip it all together, and then have it like fold onto each other.
Sure. I'm okay with that. Now, what do you want to do about the floor?
Um, for the floor, we're thinking about just like um titanium like still to going on a triangle concept like titanium triangles like laying the whole entire floor as a foundation and like having them be having like just cross beams of like titanium going along the edges of the triangles like to keep them stable and the level with the rest of them and then having like the axle supports be drilled into the ground and above the lunar surface so it's more level and usable um, for the scientists and stuff on this moon.
Sure. And so part of what I'm thinking about is so you ship up this flooring material, you ship up the top portion. Um, what kind of time does it take for the astronauts to build the floor and then be able to put the top on it? You know, is how do you see that going?
So so they could probably like split up the workload, you know, a couple astronauts working on the dome itself and then a couple people working on the floor at the same time.
Okay.
Uh, or my idea is so like the triangles are still having a folding aspect, so they're like folded together. So the astronauts first build the frame for it, and then they lay the triangles on top of it, like as like they unfold like a stack of triangles that lays into like slots in the frame.
Okay. And remember, so we're looking for as much automation as we can, right? Because these astronauts are going to be in these puffy suits and it's really hard. They're not going to be able to, they may not be able to lean down and touch their feet. Does that make sense?
Yeah.
So be aware of, start thinking about how are you going to make that easy for these astronauts that can't necessarily bend down and pick up lots of things. It's going to be difficult. Does that make sense?
Yeah.
Okay. All right. Now with the dome that you've got, what does that look like? What pieces of tape do you have to remove to be able to make it lay flat or be able to fold up properly into a ball or something?
We have to remove like on this dome as we've been trying that stuff, we've realized we gotta like remove like one half, like, so it's always connected through like one piece beforehand, and then you have to apply two pieces of tape to like
Sure. Okay. Now, and I like the size that you've got there. Does that represent if I have a ball, a baseball to roll in there?
Yeah.
It's to scale.
Okay. Now, and so I like what you're doing there. So consider if I've got a baseball, what size, and it's supposed to be a 2 meter diameter, what size does your rover need to be? Is that something that you could make out of Legos to kind of represent your idea? Um, and that, and what I'm looking for is the less imagination I have, the better your prototype is at explaining what you want. Does that make sense?
Yeah, that makes
Yeah.
sense.
All right. Now tell me about the hatches. How are we going to get in there?
Um, like you mean like the airlock?
Yeah, so you've got to be able to close that hatch. How are you going to close the hatch and make sure that we're not losing air?
Well, we're thinking about first having the airlock be a semi-inflatable, like it's like those like round things for like cats and little kids that you like pull out. We're
Yep.
thinking about those for the airlock, so it's just like it has multiple doors in it that are like sealed, and then
Okay.
about having like some redundancy, so like three doors, like there's the airlock room, and then there's like the storage for like the spacesuits and other things to just like keep the area in the habitation zone clean for the astronauts.
Okay. Well, and remember, you're so there's the garage, the porch, and then the habitat. And that porch is already an airlock by itself, right?
Yeah.
And so the garage does not need to have more airlock, but it does have to have a connection to your porch, and it has to have a door that you can seal. But you have to be able to open up that door to be able to drive or roll in uh your supply pod. Does that make sense?
Yeah.
So start thinking about so I like your idea with the triangles. How are you going to attach to that porch?
We haven't thought about that yet.
No.
Okay. And you get to design that. Does that make sense? So I don't so what I mean is whatever it is that you think that you need for on the porch is what you can design for yours. Does that make sense? I don't have to tell you what that is. I'm going to give you that kind of freedom. Okay? All right. Hey guys, I like what you're doing. Do you have any questions for us? What other thoughts do we need to be on?
We're thinking about maybe using like C-track shelving, but we are struggling with like trying to figure out how to like make that like back compactable.
Mm-hmm. Okay. Um, yeah, we use a lot of seat track on the space station, and we'll probably continue to use that, so that's good. Um, okay, so another question for you related to that hatch, right? So, are you expecting to drive this in, or are you going to roll it in, or what are you guys thinking of doing?
We were thinking about like having like it come up to it and then you roll it into the thing so the rover doesn't actually like bring in the lunar dust with it as it drives in.
And I'm okay with that. Um, so, um, is there, so when you've got this hatch and you bring in your supply pod, how do you make sure that you don't damage the bottom portion of that hatchway?
Hmm. We could
We haven't given much to the transportation aspect of this project, so
Okay. It's something I want you to think about because that's a critical component. Probably the hardest part about this project are those hatches. How are you going to close it? But also, how do you keep the dirt and the vehicles or whatever that come in from damaging that hatchway so that you still have a good seal? See what I mean?
Yeah.
So, I don't expect you to have an answer for it, but it's something that you need to be thinking about. Okay? All right. Good job, team. What do you think your next step is?
Our next step is to fully 3D model the design and get like either a 3D printed version or just like a fully simulated 3D model out there and working.
I think that sounds good. And you've got a good beginning there. You can tape and untape that thing as you like. And in some cases you might elongate or widen some of those things up. But I think you guys are on a great path. I really like it a lot.
Mhm. Yeah, and I like that you're using origami and those triangles could be a doorway. And just hinge it up or hinge it back or whatever. But I'm sure you can find a way to make it collapse totally from origami. Just keep checking that out. And one of you do research on that.
Yeah. And one advantage you have here is that it only has to go up once, right? I mean, the idea is we want to put it in this position, inflate it, and then leave it, right?
Mhm.
Okay. Excellent job, team. I look forward to seeing what else you want to do with this because I think you're on a good path here.
Yep, really creative. So thank you so much. And you can always ask questions anytime.
Sure. Send us emails as you need.
Yeah.
Okay.
Okay. Have a great afternoon.
And just double checking, you guys didn't have any other questions, do you?
No questions.
All right. Good job.
Thank you.
Talk to
Thank
you
you
soon.
so much. All right, so now we're going to move from the state of Washington to Montana and Bozeman.
There we go.
Thank you for your
So
time.
unmute, make sure that you're
Thank
mobile
you,
box.
guys.
Hit your video, and then hit share. Okay, share. Desktop too.
Good morning. It's still morning
Morning,
here.
good morning. Nice to see you
Nice to
guys.
meet you all.
Hey, guys.
So we are doing our Lunar Supply Pod project, and we're all a group of seniors from Bozeman High School. So, if you'd like, we can begin whenever you're ready.
Yeah, introduce yourselves and tell us what you want to do after Bozeman High School.
All right, I'll start and I'll let them go however they wish, I guess. I'm Jack Molson. I'm hoping after college to go into some type of neuroradiology or something with like brain scanning and brain waves.
That's
I'll
exciting.
Cyrus go.
Cyrus Geddes. After high school, I hope to get my master's in marine biology and hopefully work at an aquarium.
That's terrific.
Hi, I'm Orion Walker. Hopefully after this, I'm gonna graduate and go on to get a master's in mechanical engineering. So
Awesome.
Terrific. All right.
Thank you.
Okay. Tell us about your project.
All right. So, as you can probably see on our screen, if it's shared correctly, you can see that we're doing a lunar supply pod garage, and we've kind of split it up into 3 parts, I'd say. I'm working on the airlock portion. Cyrus here is working on the main inflatable base.
and I'll be working on the dust disposal system.
Awesome.
So I'll start with the airlock. If I can get it to change. For some reason it's not.
Okay, that's
There we go.
There we go.
All right. So I kind of started with airlock design thinking, what are some pre-existing seals that we might be able to take advantage of that are out there? And one of the main ones I thought of was, well, vault doors and, weirdly enough, water bottles. Each one is airtight in their own right, but I came up with a kind of concept that merges the two. And I kind of looked at this originally with, well, how can we make it light? How can we make it easily transportable? Being easily transportable is a hard problem to fix, but with some rough designing and some more time spent to it, I can probably make it significantly smaller. But in terms of materials, in terms of lightness, HSLA or an aluminum steel composite might be the best way to go here. It's pretty light. It gives roughly the same strength as steel, but the lightness of aluminum, which is pretty great. And I looked upon some other NASA research and data, figure out that the S038370 has been previously shown to be a working silicon seal that we can use on airlocks. So I took advantage of that pretty well. And I kind of want to put it inside of its own little grid in the same way that like you might see a small little seal in a water bottle. And then I took a look into elastomeric polymer increases, which help with seal effectiveness, which is pretty great thing to have, especially when you're, don't want to freeze to death or get regolith inside your own base or, not have oxygen. So pretty great things to have. And another thing I thought about when I thought about water bottles is that, well, sometimes you can get mold or dirt inside of the little seal. So a filtered purge cycle to remove regolith would be pretty great. And like electronic exterior door latches to make sure it's 100% airtight and air sealed.
Okay.
Next up, I will move on to my friend's turn to go really quickly and his design for the garage structure.
All right, so we're thinking on doing a semi-rigid, semi-inflatable structure with the main rigid structure be a large plate that is going to be housing this big vault door so the supply pods come in and out. And off this base will be a inflatable structure that has inflatable ribs that will inflate. So even when the doors open, the structure will still maintain its like structure and will like collapse on itself. And then when it's closed, you can re-inflate it and it'll be completely airtight and the seal. And hopefully this means when you can ship it up in one piece and it will be super easy to assemble because it'll already be assembled and you'll just need to inflate the structure. So
very nice.
Yeah, we're thinking about because damaging the seal on the bottom will have rails with wheels so that we can use a pulley attached to inside of the structure. So you can pull any structure that's not easily movable into place inside the structure without damaging the seal at all. So
all right.
Yep.
Excuse me.
Pardon me, Jack. That's fine. Sorry, technical difficulties a bit. All right. My task was the dust disposal system. That's what I've heard a lot about for this design. And my idea was we keep it simple. We have a great system inside of the supply pod. You can see I made a crude model up there with the glue stick and a laser cut piece of cardboard. The idea is we put the supply pod up there. That's what the glue stick represents more or less in scale. Then we can just use brushes to brush the dust off. It'll fall through the grate and into the collection drawer I have. You'll notice from that image that I haven't had time to fully 3D model it yet, so I had to use a stock one. But the idea is underneath the system, all the dust will be, or underneath the grate, all the dust will be collected in a drawer. This drawer can easily be pulled out so we can dispose of the dust without it clogging up the garage or the rest of the space station. Another thing I've heard about that I know the astronauts and everybody is really concerned about is getting it up there easily and assembling it without too much difficulty. For that reason, this frame will be made of aluminum because of its strength and overall lightness compared to materials. It will also have an interlocking hook system, as you can see here. Hang on, sorry, let me load the on-shape document for a moment. So the idea of this is it functions almost like a carabiner. So we have this right here, and then we can lock it into place with these so that the astronauts can do it even wearing the bulky gloves and without too much issue or needing to have a lot of dexterity with their fingers. And they can assemble it out of smaller plates, almost like a Lego set.
Okay, so wait a minute. What? Go back on that.
Oh, yes, sorry.
Okay, so I'm not quite sure how do these what is your hitch doing? Internally, I guess.
Okay, so the idea of this is we don't want to send up like one large giant grate that'll have to hold everything in one piece. So we're going to have to assemble it into smaller plates.
Okay.
Bottom of each of these plates will be one of these two mechanisms, as you can see from the middle picture right here.
Yeah.
One will hook into the other so that it's held in a solid state so that we can take all these small pieces and keep them in one piece without the astronauts having to use too much manual dexterity.
Okay. All right. Now let me go back to the drawers. How do I where do I access the drawer from? Is that inside or outside?
That'll be inside. So the airlock won't be entirely taken up by the grate system, just mostly. So there'll be a space off to the side where you can get down there, pull out the drawer, clean it out, and then you can take it outside and dump it without it getting inside to the space station as a whole.
Okay. All right. And part of what I'm looking at is that I've got a drawer that is, I don't know, let's say it's let's pretend it's 2 feet long. So that means that I have to have almost 2 feet long of space that doesn't have the grate so that I can open it and remove the dust. Is that right?
Yes, the scale is probably going to be. Actually, that's a really good thing I need to think on. So thank you for reminding me of that. Ideally, we're
Okay.
going to have a bunch of smaller drawers so we can pull them out one at a time. So like behind that drawer, there'll be another one we can slide out, and then we can pull them all out a little bit easier.
You know, just a thought for you. If if you have the flooring under the grate sloped, some of it would slide down and then you would not have to have a large drawer. Does that make sense?
Yeah, that would make it a lot easier. We can just sort of funnel it into one area and then take out a smaller one.
Sure. Now, and so how do I get those grates in there? If this is an inflatable structure, do the grates show up inside already?
So what'll happen is this is sort of a separate thing from the this isn't exactly connected to the other system. So think of it more like IKEA furniture. You don't push the couch into your house. The couch comes in a lot of different parts that you can easily bring in through the airlock, and then you assemble inside of it.
Okay, and I'm all right with that. Just be aware of how to show that with your model as best as you can. Okay. Now if we could go back up one slide, I think.
This one?
Yeah. Okay, so here I see that we've got a front hatchway, but of course we have to, so this is the garage. We also have to have a doorway on the other side for getting into the porch from the garage. Does that make sense?
Yeah. Well, this would be pretty easy because as long as the main door is sealed, it'll maintain its shape. And as long as it's connected to the main supply pod, we can honestly just use a zipper and the pre-existing hatch on the other supply
Porch.
pod because it'd already be
No,
pressure.
I agree with that. So make sure you show that in your, how are you going to have it on the side? Are you going to have it in the back? I don't have a preference, but you need to show us how they're going to attach, and you get to choose what kind of mechanism it is that of how you attach the garage to the porch. Does that make sense?
Yeah.
Okay. Now the other question I have is, so I show up with this with a supply pod. How am I've got a lip there. How am I going to get it through that door? Is this getting driven in there? Am I rolling it in there? What's the plan for how to get it in?
Well, if we like attach a hook or something, and then we just use a pulley to pull in a supply pod on like wheels or something, we could get it in pretty easily. Be like,
Okay. And so I want you to see if you can show us as much detail on how you're going to do that. And part of my difficulty here is just that pretend I was trying to roll it in. That's a pretty big lip for me to have to roll it over. Or whether, imagine if it's not a sphere shape, what if it's a cylinder shape? Is that going to be the same kind of mechanism? You see what I mean?
yeah, I'll have to think about that.
Okay. And I think you've got some great ideas here. So and you have some creative license here, right? So if we go out with some kind of with a rover, do we pick up the supply pod with a winch and then we bring it over here with the winch, or is it something where we can roll it on and off of the rover and how you want to do that. So I wanted to give you guys some room to decide what that would look like for your garage. Does that make sense?
Yeah, we could understand that.
Excellent. I think you guys have some great ideas here. How did you want to build this into a prototype? Is this going to be 3D printed? Are you going to use some cloth and do some sewing? What are you guys thinking of doing?
I think it's probably going to be a mix just because we have, like we said, the three different major components of our design. So we're probably going to have a couple of different prototypes displaying all the different things. So like the hook and the grade system are ideally going to be 3D printed by the time we see you guys again. But it might be better to use things like cloth and balloons to help show the structure of the garage itself. And then the airlock, I'm going to be honest, that sounds complicated. I'm sure you've got something.
Yeah, the airlock has some already rough made 3D printed basic models that are at my house. I still have to do some tinkering and tampering, but it should theoretically work completely by the time of the actual review.
Well, and so for example, you're talking about the hatchway. I could see that being 3D printed, whereas the main body of the thing could be made out of cloth or even make it out of a transparent plastic kind of material, like saran wrap or something, just so you can see the inside, but also so that you can see the more the more detailed your model is, the less imagination I have to have, and it helps me understand your idea that much better, right? So explore that as best as you can, and remember, if you make it all out of cloth, that's terrific because it shows how you can go from the folded position into the final position. But of course, I can't see what's inside, and so it might be that you have one that shows how it functions, and then you might have another one that shows what's inside. Is that okay?
Yeah, that sounds a good idea.
Yeah, that's a good idea. Thank you so much.
Thank you.
Excellent. Excellent.
Two models would be good to show that, because we want to see everything. I like your pulley system of pulling the supply pod in instead of having the astronauts push it in, which might be difficult. So,
anything you can do to make it a little easier on them is probably.
Thank you for thinking of that. That's awesome. And then I like your pegboard on the bottom, and you're absolutely right. You don't want 2 feet on one end. You could split your pegboard down the middle and have 1 foot on one side and 1 foot for the draw on the other side. So there's ways to get around that extra room you might need.
Yeah.
Besides what Glenn said, which is a great idea, put it on a slant. That would really help.
Yeah.
So great. Do you have any questions for us?
We do actually.
So most of these are about the door. My main concern is like the thickness of materials. Do we have a preferred limit for basically how thick we want the door to actually be compared to its final design, or the thing in that area, I guess?
Well, and that's going to be determined by you, I think, in terms of, are you going to be making this out of aluminum? Is it going to be, can you have parts on it that are rigid and other parts that are flexible to help keep it lightweight, right? So there's different options there available for you. Now, you might also want to include a window on there, just because, before you open a door, you might want to be able to see what's going on out on the other side. So these are just some thoughts for you on it.
Okay.
Yeah, and the window would actually answer your security question. It's if you have a window and you can see who's on site, that's a security issue for you. That would be a good security issue. And I'm thinking more of the weather before you open the door, but I don't think you have to worry about other astronauts.
Yeah, I don't think
they're probably
we're not so worried about Chinese attacking us so much, or Russians attacking. Although, if you've seen them, did you guys watch the series? What is it? Space Force?
Oh yeah, I did. It's funny.
Yeah. So Yeah, don't let anybody have tweezers or fingernail clippers, I guess, right? So okay, you guys go.
There's one more question.
Yeah.
Between replacement parts.
We've got a few more questions actually, if you have time.
Yeah.
Go for it.
All right, great. So I'm just going to kind of piggyback after my last question. Would something like a clear vinyl work pretty well for that door transparency?
Sure, that works just fine.
All right.
And so consider because this is a scaled model, it's really hard to put everything into one, right? So you might have you might say, well, here is a stack up of what we think the materials are that we would use for it, right? And then there might be the one that inflates or whatever. It might be transparent, and then you might have another one on the other side that that has like this is what it looks like inside, and these are some of the other materials. The point is just, what do you need to express your ideas so that you can show as many of them as possible. So you might have a number of different things to help explore that. Is that okay?
Yes. All right, I'm gonna pass.
You don't have to pack everything in one place is part of what I'm saying. Okay.
Yeah, that makes sense.
Yeah.
I was wondering about like terms of like power, electricity. Should we have a separate power source to the garage, or should we have like a way of linking it up to the main like station or area? Which would be
Right. So
better?
good question. I think that in general, there's we are probably going to have two sources of power, one of which is probably going to be a nuclear power plant somewhere, not too far away. And then somewhere else, we're probably going to have some solar panels. And this is probably just because of scaling. At first, we might be able to send some solar panels, and we're going to hold on to those for as long as we can. And then eventually, we're going to have the launch capacity to be able to get a nuclear power plant there. But for the most part, you're just going to have, one or two cables or whatever coming over for power to your to the garage. Does that make sense?
Yeah.
I can work with that. And then last one. This revolves very heavily around the supply pods. I know there was a bit of information on the HUNCH presentation we were given, but has anything been updated since then? Do we have any official models or anything we could use?
I wish. We don't yet. And so the supply pods was a suggestion to NASA, in the idea of, we're trying to minimize how much trash we send there. So you don't want to have a bunch of landers that end up being a problem. You land it and now it's trash. So by having supply pods, we're hoping to be able to suggest the idea of less less materials being sent. And yes, that leaves you some supply pods, but it's not a whole spacecraft. Does that make sense?
Yeah, I understand that.
Okay. Sorry, I wish we had more information for you. I would love to be exploring that.
That's very fascinating. Yeah. Did you have any other questions?
I guess my last question up on the screen. What is the ideal length of time that this would need to hold up between replacement parts? If there is any recommended amount of time, or
that's a great question. I mean, so for example, like the modules for the space station, we planned on it being able to be used for somewhere around 25 to 30 years, and we're now getting to that point. And so we would probably be planning on somewhere on the order of 25 years for one of these to last, expecting that someday it's going to, yes, we will replace parts throughout that time frame, but hopefully it'll last at least 25 years. Is that okay?
Yeah.
That's a long time.
It is. That's a long time to be using them.
But you can always send us questions. Don't be shy. Send questions anytime, and we'll get them answered for you. So thank you so much.
And thank you guys for your time. We really appreciate it.
It's lunchtime now in Montana, so Enjoy your lunch. Thank you for presenting.
Thank you. Have a good one.
Okay. You too. Bye-bye.
All right. So we're back
Okay.
at Billings here?
So no, we are going to Wisconsin, East Troy.
Wisconsin.
You visited
Excellent.
East Troy before, right?
I have.
Because I remember you describing the downtown.
Yeah.
So yeah, no, Billings Career Center is just listening in.
Okay, sounds good.
They presented this morning already on that.
Hi, team. How are you doing? Oh, we can't hear you.
East Troy, you're up. We still can't hear you.
Yeah, I can't hear you yet.
Nope, we still can't hear you.
He's checking.
Yeah.
Hello?
Yeah, now we hear you.
Yes. Tried to test these things already and all that type of stuff. Thank you for meeting with us.
You bet.
Yeah, and we're recording this because Nancy and Cody would like to see it too.
Okay.
Okay.
So now I gotta try to figure out how to share their PowerPoints. I saw those other ones look really nice on how they shared.
Yeah, just run your cursor down the bottom of the monitor, and there's a big green square.
Here we go.
There you go.
Okay. Oh, here we go. Does that work good? Can you see
Yes.
it?
It's coming in.
It's coming.
All right.
There we are.
All right.
There it is. Trash ejection system, it says.
Yes.
Yep.
All right, there you go. You have control.
Okay.
Okay, just quick. Sure. You guys know what we need to do, correct?
Yeah.
Yes, we do.
Okay.
One more.
Okay.
I got this one. So when we started brainstorming, we were thinking more of how to get more trash ejected at once and how to really get rid of it. So on the left-hand side, we came up with this before reading through all those slides. And so it's a bit off. So we moved on because we were thinking, oh, we can fill like one big container and eject it once we get there. But then we read more and figured out whenever it's full, it's got to go. So we moved on to our second idea, which was and kept with our first idea of like compacting the trash. So we kept with the trash compactor and added a way to move it into a different section where it can get loaded or, bagged of some sort into other stuff.
And then get sent out to space so we can get rid of it.
Okay.
But then we realized I was taking up a little too much space, so we simplified it into a little more compact and a little more like our final design. If you go one more slide, I think it is.
Okay.
Oh, one more. Nope. We really missed this.
Yeah.
This is the final model we have as of right now.
Just half of it, really. Well, it's as much as we want. Yeah.
Anyway, you want to explain?
Anyway, we decided to use hydraulics to help compress the trash.
Okay.
And so the astronaut would put the trash in. The first hydraulic would crush it and bring it to a certain level. That way it would fit out an exit door over here. And then a secondary hydraulic would push it out of said door.
Okay.
And then into the vacuum of space.
Okay.
Good demonstration, guys. I like it.
Yeah.
So, all right, but we're trying to figure out how to eject the soup can. How do you want to do that?
We're thinking as this isn't up to scale really. This is just like so we can have a physical model, see what if anything would like really jam up or not really work. We're thinking because we're going to store it into a different container that because it's going to be in a different container, it'll be easier to eject because it won't be as round.
Okay. All right, that's going in a different direction. I'm not sure how that's going to work out. And don't get me wrong, we definitely want to have some kind of trash compaction, but that's a completely separate project, and unfortunately, it's more difficult than what we seem to think sometimes. Let's see.
Do you want me to change the slides?
Yeah, sure. Let me
Yeah.
see what else you got.
Go back.
Wrong way. Come on.
There we go. Okay.
One more. Go back to one more design.
One more? Okay.
Come on. You got this,
The,
Andy.
the little thing, it's not going. I'm sorry.
Technical difficulties. Give us a second.
You okay?
It keeps hitting the drawing thing. There's a little drawing thing that keeps messing up in front of the arrow.
There it is.
There we go?
There we go.
Yeah. Okay. Sorry. What were we talking about?
But you were saying we should focus more on the ejection system, ejecting it out into space as the main.
So compaction is definitely a desirable thing. However, right now we're really much more interested in just trying to figure out, I've got trash, how do I get rid of it? And so one of the things is like, for example, the poop container, right? That's one of the things that we definitely want to get rid of, right?
Yeah.
I don't want you to have to compact the poop container.
We were thinking the compactor would only be used for hard trash. For soft trash, we were like gonna do something like the soup can where we just put it in a container and then shoot it out.
Yeah, it skipped the whole like compacting system. It skipped this section and just go straight to the push arm that pushes it through.
That's right. And part of the difficulty with the trash ejection is, how do I deal with those hatches? Because here I've got a very small airlock where I've got to have both of them sealed, right?
Yeah.
And the other difficulty is that I want to release it without losing air. You see what I mean?
Yeah.
Go ahead.
Oh, I was gonna say, there was on the slides, there was a example where you guys used a torpedo, and what we were planning on doing was taking a vacuum and removing all the air from it before we shot it, and then we would use that same kind of system to shoot it off.
That's exactly right. And there are many ways to do it, whether it's a spring load or a motor. You can even use like a pneumatic system, but we don't want to lose very much air if we can handle it, right?
Yeah.
So yeah, you can do lots of different ways to develop that.
Yeah. Okay.
So you have more slides to show us?
No. When I was making the presentation, I was going off a template and I forgot to get rid of a couple more slides that I needed.
Okay.
That's why the formatting was so weird too. That's my bad. I'm sorry.
That's okay. That's okay.
Show me your prototype a little bit more. Let's stop with the presentation.
Want me to show it closer?
Stop sharing.
Oh yeah. Do you want to do that? I don't know how to. I did.
Yep, no worries.
Give it a second. Yeah, I'm sorry about this.
You're fine.
I'm just saying sorry. It's taking up more time than.
Yeah, just run your cursor and it will show. Yeah, and stop sharing.
You open the Zoom.
Yeah, and then
shouldn't say stop.
Does that work? Am I still sharing?
Yep.
Yeah, you're still sharing.
I'll say, what did you say to do?
Well, I just wanted to see a little bit more of your prototype.
Yeah,
no, to get rid of the sharing.
Sharing. Run your cursor, take your cursor and run it, and there will be a big red thing that says stop sharing.
I think it's at the top.
It's up at the top.
It's the little recording thing, I think.
No, that's recording.
That's okay.
Screen. There we go.
It's the X at my screen thing. Yeah.
You just X that out.
Yeah.
There you go.
Okay.
Yay.
There we go. hold this again really quick. So what we have is a simple comes down and then this comes through and pushes it that end.
So let me ask you about that. So how would you, what kind of mechanism would you do to do the compressing?
We thought hydraulics of some sort.
Okay. Well, and imagine, I'm not opposed to hydraulics, but consider if we have a leak of hydraulic fluid at some point. That could be bad. What other method could we use besides hydraulics?
Pneumatics or a gear system.
Sure. And so we've looked in there was a time when we had a trash compactor on the space shuttle, and they actually made it was a geared system, and they would move these paddles back and forth. You know, you can imagine if they have a crank one, you know, they would twist unless they had their feet attached or something like that. And what else did they have? We were looking at a way to be able to use a drill mechanism, just pick out a drill and attach it to it, and then we could use that motor to do the compressing. Does that make sense?
Yes.
What happens if you've compressed it as much as you can, but it's not small enough for the ejection door?
We were planning on making sure that it'll only be full if it's able to go into the door. So if it can't compact it, then they're probably going to either have to like make sure that they're doing it on a good routine, or like they're gonna have to take trash out, which we want to not do, but we're hoping that a good routine will just make sure that everyone's good.
Sure. Okay. Now consider, so you've compacted it, and you're ready to push it out. How do you want to open that door on the outside of the spacecraft?
We were thinking some sort of like door that comes in. That way we could use the pressure of the spacecraft for when it isn't, like when we don't pump out the air, so we can use the pressure to seal it better. So a door a door that comes in and slides up, maybe something like that.
Okay. And so how do we operate that from the inside of the space station? Because we don't have to do an EVA to get rid of trash, right?
Yeah. Just some sort of like screen or a simple button system.
Consider when I was a kid, we didn't have electric windows on our cars, right? We had a hand crank system, right? And so one way you could look is, how do you operate a car window?
Yeah.
Does that make sense? Because you don't have to go outside to roll down a window. That wouldn't make any sense.
Yeah.
And you could probably do a YouTube video on that, so just a thought for you, because those have a hand crank, and you could do it whether it's with a motor or a hand crank.
Okay.
Now, let me ask you about your piston to push it out, right? So now you've compressed it, you've opened up your door, and now you want to push it out. How do you keep air from coming out with it? Because you've got like some kind of a piston that's going through to be able to push it out, right?
We were thinking something along the lines of like a vacuum pump, because what you guys stated in the directions, it says we can use one. So we thought that would be the quickest way to get rid of all the air out of it.
Sure, and that's definitely what we want to do. Hold up your model again, though. Okay, so in your right hand, you've got a handle that you're going to push on, and that handle pushes through, which means that I've got a leak right there. Do you see that?
I was just using this because we thought we could use hydraulics and they would be internal. And so this was just to show how the hydraulics would move.
I see. Okay. So your hydraulic system would be interior as well. Is that right?
Yeah.
Okay.
It'd be held inside.
This was just the example.
I see. Okay. And so now there are ways to do that, right? Because if you saw the pictures of of Skylab, they had a method to be able to push it out even though they were inside. And so you can look at some of those examples as well. Okay. Um, I like a lot of the things you guys have here. I think you guys have some good ideas for how that trash can be ejected. Yeah, we don't right now. I want you to concentrate more on the ejector than the compaction. But you're definitely correct that we need to have some kind of a trash compaction at some point as well. So I was trying to keep it from getting too complicated. One difficulty with having the trash compactor is that yes, you've compacted the trash. Once you eject it, unless there's a lid on there, you may end up having some stuff floating out and being another hazard. Now, to be realistic, there's we've been littering our planet for a long time, right? We've been littering our space around our planet for somewhere on the order of 50 years or so. Imagine how long it would take before we would expect to run into trash when we're going to Mars, right? There's a lot of space. And so, however, there is still a concern of, do we really want to pollute all of that space and then run the risk of, whether it's the Enterprise or whatever, getting hit by a space toilet tank or something like that. So
our plan is that we would cover all the trash in like an aluminum bag or container or something, and then we would shoot it towards Mars's atmosphere, and it would eventually get burned up as it goes around.
And that's what I hope as well. Yeah, I don't really want to run into poop containers and things like that in the future. But of course, if we miss Mars, which is very possible, it's something that we have to be thinking about. Yeah. But you were thinking of like an aluminum container bag of some sort?
Yeah, some sort of bagging system that we haven't quite figured out yet.
Yeah, and that's actually a terrific thought, right? So, for example, we are going to have a certain amount of soft trash that's not going to be in the toilet, right? Yeah. And that's a lot of what you were thinking about in terms of the soft container. Is that correct?
Yes.
Okay. And you guys are thinking right. Right now on the space station, we use a 9-liter plastic bag. Oh, Flo's got one. This is awesome.
Yes.
And I'm not sure if that's exactly the right size, but it's pretty close.
I mean,
hold that up so that they can see it. So it's a Sea to Summit plastic bag. There you go.
There it is.
So I think that's pretty close to the right size.
Yeah.
And so if that's the kind of thing that you guys were thinking about, you're on the right track. Some kind of a plastic bag, some kind of a bag that we can compress and turn into the thing that we throw away. I think that you guys are thinking in the right direction.
Yeah.
So, and how much do you think, have you guys done any trash compaction?
Not
currently.
yet.
That's the next step we were thinking of taking.
Well, and so you can there are commercial trash compactors for your house, right?
Yeah, I do believe so.
I've never owned one, so I've never tried it. You can imagine you can put some trash in and compress it, and then you put some more trash in and you compress it. You can imagine that depending on what you're putting in there, you're going to have a little bit of
pushback,
re-expansion afterwards, right?
Yeah.
And that was one of the things that we were talking about when we were working that project. Just because once you've put it in, now you have to pull it out and you have to close that lid up. And so there's a little bit of re-expansion, I guess is the way to say it. I don't know how much we have to worry about it, but it's something that is an issue.
Yeah.
So anyways, wow.
So do you want them to be testing with the to the can to shoot the can out?
Mostly I want to see how are you going to shoot the can out, and so they should be able to show us how the can ejects. And hold on a second.
And it could be manual and electrical.
Yes, it can be manual. You can use springs. You can use a pneumatic system, as long as you're not losing air. And so here I got tomato sauce here, and so so that's a 3-inch pipe, and it fits in there real easy. And so you're looking for, what kind of there's like 3 different doors you can do that I can think of. All right, you can do a door like this. You can do a door like this, and then of course you can do a door that slides back and forth, right?
Yeah.
Now, do you want to do that on the opposite side as well? Do they have to be the same? Do they need to be different?
For the trash compactor, we would have to do a door on both sides because otherwise the garbage would be spilling out into the actual container.
You're right. And it doesn't have to be on this side, right? The way you guys did it was you had a top door, and that's perfectly fine as well. So I think there's some really good options for that. Okay. Now, wait a minute.
Yeah, I like the top door. That's a good option.
Hold on.
But I also would like that some kind of warning light on your device that would tell the astronaut, hey, the outside door is open. So don't,
open up anything because then yeah.
Right.
That would definitely be a necessity.
Now, I mentioned a pneumatic system, right? So one way to do it is you've got your soup can and you've got like a cylinder, and you could use the air pressure from inside the spacecraft to push it out, right? Because if you suck the air out of here and then you open the door, then you can open a valve here, and the air pressure from inside the space station will push it out by pushing on the cylinder. Does that make sense?
Yeah, it would suck it out.
But you haven't lost any of this internal air. So just some different options for you guys.
Yeah.
Thank you.
Thank you.
Now, it looks to me like you guys have a laser cutter. Is that right?
Yes, we do.
Yeah. And I like how you did your model because, you start off with some cardboard and you start expressing your idea. I think that's great. What do you guys want to do for your next one? Do you want to stay with some cardboard, or do you want to start working with other materials?
We'll probably start working with some other materials starting at soon.
We do have access to 3D printers and stuff like that.
Excellent. And don't think that 3D printers are the first place you have to start.
Yeah.
So for example,
I feel like my life is
so prototyping is really research, right?
Yeah.
Because you're practicing to see what works and doesn't. And so I like to pull out any time that I can go to the hardware store or go out to my garage and find things that I've forgotten about, right? Finding off the shelf kind of hinges. Now, if you're looking for torsion springs, you can always steal them off of a rat trap. Just be careful you don't rack your knuckles like I have, okay? But I also find a lot of springs and things in my garage. I don't know if your dad's like me, but I got a lot of stuff in my garage that I've forgotten about. and my wife would like me to get rid of them. But you are the excuse for why I haven't thrown them away, because so anyways, just things to think about. Anyways, do you guys have any questions?
Currently, you answered the only couple I could think of when we were helping.
Okay. Well, one more thing here, right? So, where's my suit? I also use my recycle bin for a lot of stuff. So, for example, here, this is some a box for nuts. And notice how nice the can fits in there, right?
Yeah.
So that has room for my can as well as whether I have a pusher plate and some springs and things like that. But it's also really lightweight, and because I can see inside, it makes it easy for me to be able to use it as a display item, right?
Yeah.
So these are just some other thoughts. You don't have to do what I'm suggesting, but
It
they
would
might
help
give
us
you
know
some
the idea.
ideas.
Yeah.
Yeah.
Yeah. So your next prototype doesn't have to be 3D printed. Go to your garage and find some.
Yeah, I have plenty of scrap stuff sitting around.
Yeah.
Okay. All right. Any other thoughts?
I think we're all good here, right?
Yeah.
Yeah. Okay. Thank you guys again for
Awesome.
All right.
Keep
You bet.
working. Yep. You guys have a wonderful afternoon now.
You too.
Thank you so much. So there's another team, right?
I'll go.
Oh, excellent.
There's I think 3 more teams. Good.
Okay.
I think it's after school already there.
Oh, is it?
No, we're during school right now.
Oh, okay.
Oh, you're still in school?
Can you tell the guys?
Yeah, we're going to talk right now.
So, yeah, we're still in school, but I actually have my IPLTW class kind of surveying them, explaining their projects because they're starting an introduction to engineering design. So it's like, oh, it'd be good. Little field trip.
Oh, so those are your students in the class.
Yeah, behind them are some of them.
Yeah.
Yep.
Future HUNCH students, I hope.
I'm waiting for them.
Now, this next one's a chest from trash one.
Okay.
Hi.
Hi.
Hello. Oh, let me check that. There we go. Okay.
No, I don't sit over here. I'll just put myself down. Slideshow.
Okay.
Hi. We're getting our slideshow up real quick.
Sounds good.
You could introduce yourselves before that goes up there.
Okay. I'm McKenna. I'm a senior. I've done HUNCH for 3 years now.
I'm Zach. I'm also a senior, and I've done HUNCH for 2 years now.
Awesome.
That is terrific. What did you guys do last year?
And then Tyler, introduce yourself.
Oh, hello, I'm Tyler.
Hi, Tyler.
I've been for 4 years.
4 years.
No.
Holy
2,
smoke.
3, and 4 years.
Okay.
So we were in a group together last year and we did the copper heat transfer project.
Oh yeah. Okay. That's really cool. All right.
So we're just getting our slides up for our chest from trash project up right now. I think Mr. Mansky's getting them up.
Okay.
Yeah, it's definitely a transition going into this project from the last one because it's just a completely different testing process.
It is.
But it's still really fun.
Good.
Oh, look at that. Is that you guys right there?
No,
Some of
that's
your
not.
ideas?
No, that one's not us.
Okay. That's very creative. So that's interesting. That's some good inspiration. I like that.
Yeah.
Okay. What do you got?
All right, so immediately following what we did when we met with you guys the first time was we knew of the constraints that we had, which was the printer sizes being a certain one smaller than what we have. And so first thing Zach did was basically size it correctly in Tinkercad, which is what we used, in order to figure out what we were working with. So you'd explain how we
So I sized the board, so we'll have 4 pieces that'll all connect together. With the inner chessboard being a 4x4, and then like the outer being a 6x6. And then we'll have those connected together to form like an entire board. And then the outside gray around there will be where the pieces can lock into. So there'll be holes there, depending what we do for our final locking mechanism, that the pieces will go in on the sides. Like where that gray
For
is.
storage, like when you capture a piece or before setting up.
Very smart. Good job, team. I like that a lot. Okay.
So then this is what we showed you the first time. This is the first interpretation of a prototype, which was just a simple kind of locking mechanism, kind of similar to like the child locks on medicine bottles, where you have to press down and slide them. So we already showed you that, and then this is where we got into stuff that we did now.
So the first thing that we ever did was we decided just to go a simple route of having the chest piece and then a direct hole that you could stick it into and then just twist it, and it's thin enough so that it would just lock. So as you can see on the board, this is a more like in-depth look at it. And then we actually printed it.
I'll bring it up to the camera. So then we actually printed this one here. It basically just goes in, we cut the hole with Tinkercad, and then this piece can slide in there. Right now we're just focusing on making the locking mechanisms before we figure out that recycling piece for the tops, because this is that anti-gravity, like actually playable factor.
Okay.
So this obviously, because when you put it upside down, it just falls out so it doesn't really work for the whole ISS anti-gravity idea, but it was just
Right.
that first step prototype to see how we could get big, we could make the hole on that square.
That's terrific. Okay, I like that idea.
So then for them prototype 3, we decided to do, we mimicked the XLR clip, which is what they use for, Zach knows more about that than I do.
Like audio cables.
Yeah.
You can send lighting through it as well.
Yeah.
Those are pretty secure. So we looked at that.
And we mimicked the 3-hole prawn, that quote unquote prawn of it. So then basically, instead of having just one circle going straight down, we used 3 of them. And then, you want to take that one up too?
Yeah, I'll take this one up. So then this one, oh, I dropped it, my bad. Oh, okay. So then we printed that one. So you can see on here, I don't know if you'll be able to see it. We do have the hole with the 2 smaller ones in it. This one, it takes a little more force to clip in.
Okay.
And then, just a moment. And then once you get it in though, when you are holding it upside down, it's stuck in there. So it's secured. So it's not going to float up or fall.
Here, show me that again. I want to see the
Like this? Or did you want me to take it apart?
take it apart so I can see that again.
So it's apart. And then on the inside, we do have it's like beveled basically. So it has the top ring and then
back up
like,
just a little bit.
I'm
It's a
trying to
little
get
bit
it so-
blurry. There you go.
So it's like beveled, so the top is a little bigger than that initial base piece that clicks in. And then on the inside, it attaches to that smaller piece. And then since it's resting on top, it like makes a clip.
Okay. Very smart. So it's more of just a friction fit rather than a twist lock. Yeah. Very good, team. Keep going. What else you got?
So then basically that's kind of all we did so far. And then we come up with other ideas. So we were thinking, okay, if you have the friction one of just kind of sticking it in, we're going to improve the mechanism, which is where then we were thinking, what if we combine both the prototype 1 and prototype 3? So instead of it bringing just the friction on the prawns, what if we add little edges to the prawns so that once you stick it in, you can twist it, and then the prawns are actually underneath the tile itself. So that way for extra kind of strength so that they don't fall off. And then basically we kind of decided on our theme of Star Wars, because obviously if you're an astronaut in space, for board games, you don't necessarily want to be reminded that you're an astronaut. You want an escapism. So we decided and locked in on that theme. And
That's
then,
fine.
And then we have the connecting the 4 pieces of the board together. We still have yet to figure out like the locking mechanism of the board itself compared to the board of each of the pieces. And then obviously for whatever, like in order to, like McKenna said, wherever you store your captured pieces, it would be the same locking mechanism as it is when you move the piece, just to kind of keep the design the same. And then obviously we have the testing trials of the drop test, and then obviously reinforcing the locking mechanism depending when it falls, how it works with the chessboard. Like if it breaks, then obviously then we gotta go back and switch to a different locking mechanism.
But as you guys know, it's not just about the board staying together and it breaking. It's also that important part of when you put the piece in and they continue to play, that it'll be secure so their game isn't tampered with as they play.
That's right. Well, and one of our problems is just the 1/6 gravity, right? Because we're on the moon, and because there's so little gravity holding it down, you can imagine if one of the people sneezes, you could mess up the whole board with that little of gravity. Does that make sense?
Yeah, and that's why we're putting so much effort before this recycling component into that locking mechanism, because I feel like that's something you guys could take further with their recycling. I think
Yeah.
the most important part that we're focusing on is making sure that there's a piece that ensures the pieces will stay on the board, and then a way to store it that's efficient.
I think that that's very smart, and I like, and so make sure I understand this. You're making the board so that my captured pieces fit around the outside.
Yeah.
Is that right? Okay, and I think that's terrific. I'm glad you guys were thinking about that. So the one that you're going to present for us is going to be made out of recycled materials. Are you trying to do only 3D printing, or do you think you're going to have anything else besides 3D print?
Right now, with the locking mechanisms, we're definitely focusing on the 3D printed recyclable filament, because at least then we are including a recycled component. But as we move forward and once we secure that lock mechanism and have that like fully workshopped and done and how we're happy with it, then we could change the tops, because basically the plan could be to attach the locking mechanism to the bottom of literally anything you want for this recycled trash. Like you can take that top piece of the lock, the board would already have the base of the holes, you just snap it onto anything. If you get 8 of any piece of trash and you attach it to the locking mechanism, you can create your own chessboard as you're there.
That's very smart. I think you guys are on a very good path there. Okay. And so you know that you can purchase some recycled filament. Is that right?
Yeah.
Okay. Do you have an idea of colors?
Colors, I think that's something that we're just gonna play around with. Like the boys said, the Star Wars theme is pretty fun right now. So I'm looking at some blacks, blues, purples, I think.
That sounds good. All right. And why did you choose Star Wars?
Basically just because, well, we kind of figured, might as well play with the space theme, but like we said before with the escapism, well, Star Wars is space themed, so might as well kind of include that. And
Popular movie the boys like. I mean, simple as that. I've never seen it, so I'm just gonna run with whatever they say.
Well, and I was going to suggest, I was just watching Stranger Things last night, which could be fun as well.
That's gonna be fun. I've never seen that either.
Well, and consider, what if you could, we just had Thanksgiving, right?
Yeah.
What if I did my family versus your family, right?
Yeah.
So just so you know, my Uncle Joe, he is quite the rook. Whereas my aunt Melissa, she is one kick butt kind of lady, but I think she'd be more of a bishop than a queen. You know what I mean?
Yeah.
But think of all of those cousins that would make terrific pawns. You see what I mean?
Yeah.
So you can steal my idea or you can come up with a better one. Okay. Okay. So who's the better chess player?
I used to play chess with my brother when I was younger, but we've never played against each other.
Why did you choose to do chess?
I think it was just a nice transition project because the copper heat transfer was definitely very intensive.
That was tough.
That was a hard one for us. It was very intensive and science-based, so I think the chess one is something we're able to be more creative with and have more fun. It's our senior year, our last year in HUNCH. It's definitely just a more creative, fun project.
Yeah, I think it's more like hands-on with like the 3D printing and the locking. It's more of like a kind of a different kind of thought process than with the copper one.
We were focused on data collection. This is something we can more brainstorm and talk about and have fun.
That's great. I'm glad that we can offer some differences for you. That's terrific.
Yeah.
Okay. Any other thoughts or questions? One more thought for you. So if this is 12 inches wide and then it's 12 inches the other direction, but you can do whatever you want height-wise.
Okay, cool.
Just an option for you to think about. Okay.
Is there any component on it needs to be stored in a way that's flat for like stacking in the space station, or does it matter like if this is just going to be sitting on a table or in a drawer, would it really matter for shape? Like if we have those pieces sticking up on the sides, is that an issue where you wouldn't be able to stack like other things on top?
Well, that's an interesting thought, right? Because we're going to be making this on the moon.
Mm-hmm.
So that doesn't mean we have to package it for shipping, Does that make
Okay.
sense?
Yeah, that makes sense.
So I'll let you guys decide how you want to do that. Okay?
Sounds good.
Yeah, good thinking.
Thank you.
All right. Anything else?
No, I think that's it.
All right.
your
Good
time.
job, team. I
Thank
can't
you.
wait to see it.
Enjoy this project. It's a lot of, sounds like you're having a lot
Yeah,
of
this
fun.
is a good one.
Yeah. And play chess. And you absolutely need to watch Star Wars. It's a classic.
I will.
Okay.
We have more from there.
Do we? Okay, good.
I have them down 4 times, so.
Okay, are we all going in a row? There's nobody in between us, is that correct?
Right.
Okay.
We're still sharing my screen, correct?
Yes.
No, now
Well,
we
we see your class.
Yeah, we see classroom.
Okay, so we're
The class.
all right. You guys are up.
We are up.
Yeah, okay. All right.
Good job.
Thank you.
Good afternoon. Hello, everyone.
Hi.
Hey, team, how are you doing?
Wonderful.
Okay. What are you guys working on?
The lunar sample container.
Excellent. I can't wait. And who are we talking to?
I'm Haley.
Hi, Haley.
I'm Riley.
And I'm Ethan.
Excellent. And you have a prototype there as well, so I can't wait. But you're waiting on slides, is that right?
Yes.
Yes.
Excellent.
It's coming up.
I don't know what order the slides in, by the way.
It doesn't really matter.
It doesn't matter.
Just talking whatever we want. Fucking circles if we have to.
We love this.
Lunar sample container. We can see it.
that now, correct?
Yes, we see it.
Yep.
Okay, are we good to start?
Yep.
Okay. So at first we kind of started brainstorming just random ideas. So we had like gaskets, vacuum sealed bags, like a wedge shaped door, like airplane doors where it's
Like an airplane door where it's wedge shaped, so the higher pressure pushes the door into the frame of the airplane, forcing the door shut. Or like a submarine, which is the reverse. So originally I was thinking about airplane doors because I recently saw something about it. But then when I think it was Riley who pointed out that submarines are actually more what we want because that's a lower pressure inside and a higher pressure outside.
Very good.
But we kind of moved away because one of those doors have a bunch of like mechanical mechanisms on them, and that's just excess stuff that you don't want.
Okay.
What was my next slide? Oh, so this was our first time meeting. We brainstormed kind of what we needed. So we kind of got with the idea of like a cylinder shape, as seen. So it will fit 2 samples. It will be big enough where it like can fit oddly shaped rocks too, just so you can fit the glove in and the rocks at the same time.
Sure.
So we did some rough math for how big we were going to do it because one of the things we were looking into was basically like a dog paw scrubber. I don't know if you want to put the
A dog paw scrubber. So wait.
Yeah,
I don't know how to hold this, but it's like this. It's got these little rubber like fingers on it. So where you can shove the sample in it and it'll get caught on these and kind of not move around because coming back to space, you got a lot of turbulence.
Yeah, so we purchased one of those and then we shoved a baseball inside the container and just vigorously shook it around and the baseball just stayed in there and like didn't move at all when we shoved it in there. So we're like, that's actually a really good idea. And we determined our size based off doing something like that and how big of a sample, like a baseball size. So we determined probably a little large, like a 6-inch PVC pipe to be for our housing container. And then we realized we're gonna need a bigger dog paw scrubber to fit to add enough cushion. So we decided to do a little bit of testing with a cardboard tube that we created.
Okay, let's see that.
The cardboard tube.
So inside, I'm gonna move this a little
steel.
closer. We did steel wool on the inside here.
Okay.
To try with that because one of the things we saw that the Apollo missions did was they used like a metal mesh, and so a metal mesh is just basically steel wool. So we did something like that, and it works kind of well.
It works kind of well. It's just there can be possible contamination because steel wool is stringy, so it's like something can fall off and get caught on the rock. So that also brought us to like extra protection, which is like a bag where you collect the sample. So it will be like another layer in the container. So if the container fails itself, it won't be as bad almost as like it would be in a bag. So like the container fails, this would help save the sample more because hopefully it would be more airtight.
Yeah,
and that adds another step to the collection process to avoid contamination, so they don't have to put it directly into.
Hold on a second. Hold on. Okay, say that again. I couldn't hear because of the other announcement.
So the bag is like another step to our collection process, so they don't have to put it directly into our cylindrical container. The bag is like another anti-contaminant step. And
I think that's really smart, and I also think that that's accurate because for several of the you can imagine when the astronaut bends down and she'll say, "Hey, this is the rock that we need. I'm putting it in bag 12510." They zip it closed and then they drop it into your box, right?
Yes.
And then she'll say, "Now I'm putting it in box 12414 whatever." So I think you're doing the right thing. Keep going on this.
So we first started with like a zippy bag, just to do that. But we also had the idea of possibly like heat sealing it, where it would be an actual plastic bag. And then you have a sealer either, I think, on the outside of the container, so it's just there and easy access. And you can put the bag in, seal it, and it'll be airtight, nothing can go in, and that could be even better to prevent contamination. But the one thing is, how does a heat sealer work?
So the sealer we were thinking about using is kind of like one of those vacuum bag container things where you seal one side of the bag is closed, you put your stuff in it, and then you put it in there and it sucks all the air out, and then it melts the two sides of the bag together. And since you're on like the moon and there's basically no atmosphere there, we can just seal the bag and it will already be air quote vacuum sealed because there's no air there to have to suck out. So we can really just melt the bag. And because we purchased one to like look at and take apart a little bit, but it's really just two metal plates that come together. So I believe there probably won't be too much heat spreading also in a vacuum.
I think you're right. And okay, so the geologists have said that they are trying to minimize the number of materials that we touch the rocks with so that we're not contaminating them and putting something on them. So, for example, the plastic bags that they're talking about using are Teflon, I think. Now, one difficulty with Teflon is that it's a high temperature plastic, and so it may be more difficult to heat seal it the way you're suggesting. But it's worth checking to see if you can do it, because I think you're smart to suggest let's put them in a bag, and if we can seal that is a double seal against contamination. So smart idea. Okay.
What about using the heat during the sun time on the moon?
Ooh, that's a good point. She's using the sun's heat on the moon during the day.
It's 250 degrees Fahrenheit.
Right.
Yeah,
that's true.
So could you concentrate it?
Well, I mean, if you used like a magnifying glass or something like that,
that would be
cool. But at the same time, that means that I've got to carry around a magnifying glass with my spacesuit. So I don't know. I'm not opposed to it, but it would, what if is it something that could be part of the box? I don't know.
Like have it attached to the box somehow, like a handle has to be attached to the box.
So like a little magnifying glass keychain on the handle.
Yes, a little keychain.
So I'm not opposed to it. Go ahead and kick it around a little bit and see if there's a reason to do it.
We also had like gaskets. the original container had a gasket, but just to actually make it a better seal.
Definitely. I think that's a great idea.
Yes.
And I see you've got some good ideas there.
So the original containers they used had like a vid-on gasket that then the box like sealed itself to by pushing down into it. So part of the idea was since we're gonna try and make ours out of a PVC pipe, we would be using a PVC pipe end cap that would screw on and screw off. So we would probably need some form of gasket to actually seal that fully. But then again, I haven't played with PVC a lot that big, so it might just naturally seal itself. I don't know. That would be further testing.
So yeah, that's our next prototype is a PVC pipe that's roughly 6 inches in diameter, and then we'll actually build it and actually be able to test with it because our cardboard is cardboard. It's not not sealed well, so it's not very good at testing with testing it. So we also have that. Another idea was like a clip lid. So I believe the pressure wouldn't affect it because once you put the lid on, it's not airtight, so air can still get in, but space doesn't really have pressure, so it doesn't really matter. But you clip it and it will just seal it airtight. It's leak proof and everything. So there was also that idea, but can't really. I don't know if you can do that with PVC. Can you?
So I like your PVC idea.
Please report to the main office. Tatiana Rodriguez, please come down to the main office.
Okay.
Okay, so I like your PVC idea, but I also see that jar that's right next to you, or that's on your slide. I mean, if you go to the grocery store or someplace and you find some jars that have some of that similar capability, could they be a beginning point for your container?
It would be good for testing.
We should get that for testing.
We should get that for testing.
We'll look into that.
We
We'll
will
look
look
into that
into
on
that.
top of our PVC pipe.
Yes.
Sure. And I'm thinking that I have some of those like for flour or rice or something like that, and it has a similar kind of clip. And I think I can get them in a variety of sizes. So just something for you to think about.
Yeah, and even variety of material because usually they're glass, but they can be plastic also. Don't get glass, use plastic.
I do also know that there are some alcohols that are pressurized that have lids like that. So it can keep pressure out. So we know that for sure, at least. I don't know if it can keep pressure in. But.
Yeah. What else do we have on these slides? Oh, this was more research. So like a plug design like that, one lid, but we like our actual, why did I go back? Nope. There. So this has like what we would want the actual container to be made out of because PVC realistically probably not the best material. It's a little heavier on the like just heavy.
Right.
And plastic is probably not the most durable container either. So probably magnesium or aluminum because they're both lightweight materials and or metals technically that are easily malleable and are very can withstand like good pressure change. So we had that, but the one thing with magnesium, it is going to need a protective coating just because of
how reactive it is.
Yeah.
Flammability. Yeah. No, and there's good reasons why we should be looking at other materials besides just aluminum. So that's good thinking. Just for your reference, the engine blocks of VW Bugs were made out of magnesium. The engine block, isn't that crazy? Okay, keep going.
And for like the handle, because they're going to need a handle to carry this, we were thinking a T-shaped handle because it's just easy to grab, have two fingers on each side, and it's just easy to hold, or a collapsible handle where it folds into itself so it's not in the way when you're like transporting it. It's not sticking out randomly, poking out. I don't know. So it's just not poking out.
Those are great ideas. So yes, you want a handle that is easy with the gloves. And you know, do you want it on the top or do you want it on the side?
There's a picture somewhere in here. Wait,
It's
sorry.
backwards.
There it is. So this one, what picture? The left bottom corner, we have like a few ideas drawn where the handle, there would be almost two handles because we had a twisty lid, so you would need a handle to twist the lid, but also one on the side where it just distributes the weight, I believe, better because it's on the side instead of on top where the rocks would be on top of each other.
So do they have to be rigid handles? Can they be foldable or could they be cloth?
I don't necessarily know for the pure fact that I don't know how cloth reacts with the temperature change. Do you know?
I mean, spacesuits are made out of.
They are made of cloth?
Yeah.
Oh,
Well,
so maybe
made
we
from
can do
cloth.
like a almost spacesuit fabric-y cloth where it can just be flexible.
That's right. And so, and also now I'm going to walk it inside to the spacecraft, right? Now what are these stackable? How do we want to, you don't have to come up with how they're going to be stacked inside the spacecraft, but you should be aware of, what kind of possibilities of how do you want to position them in there? Does that make sense?
Yes.
I think that earlier photo we were talking about stuff like that.
Which one?
The earlier one we were originally brainstorming, like a tube thing. I think you need to
Oh,
go
like
backwards
put it
on
in
the
the
slide.
wall?
Yeah. I think it's
Okay.
earlier in the slide where we were talking about that. But
Where
I don't
is
remember.
the mouse? How many containers would you say you would bring? Because I feel like it could range. Like since they're cylindrical, you can stack them almost in like a pyramid way and have a
Sure.
strap on top of them like that. Or if you're like, I can't find the mouse.
Well, consider what if might they have them? You know how they used to put milk bottles into like a milk
Oh.
crate.
Yeah.
So
they had like a handle on the crate and then individual sections for each one.
and let's pretend that they want to collect, I don't know, 20 samples.
Mhm.
And so I really have no idea how many they're going to collect, right?
Yeah.
But it's a matter of how much do they have room for. And so put that down as an estimate in terms of how many of these containers might you be taking home. Okay.
If it was like at the beginning, if it was like just one sample, we had the idea of it somehow hanging on the wall. Like since it's cylindrical, you could like press it into the wall somehow into like this plastic.
We were thinking like a Lego figure's hand that's like a C.
Oh yeah.
Like that, and then you could just like click it in, and then you would have to put a strap around it to actually hold it in place because spaceships shake a lot. But
That's a good idea. I'm not opposed to that. And yes, we're going to have more than one sample, but I have no idea how many. So try to show that you have options of how it could be located in the spacecraft for launch. Okay?
Okay.
I don't know where
Go back forwards now.
Where do I want to go?
I don't know. Forward. See what else we got. Anything after this slide?
Oh yeah, there's that. Oh wait, why is it black?
Well, here, show me more about show me more with your prototype. Oh, there you go. Okay.
So originally just with this tube, we made it double-sided because you don't know if you're going to be collecting the samples at the same time. So, so you could like do it on both sides, so you didn't have to remove a sample, or well, you won't have to remove it, but just that it would be like we would have like a extra padding in the middle of the tube, and then have both sides be openable, so there's padding between the samples. Because they're going to probably still move around a little bit, but the chances of them hitting each other would be greater without padding in the middle. And it's going to be irritating if you have to remove padding from the middle on one side, stick the rock in, put it back in. It's just extra work for them to do.
Okay. So let me ask you this. So you present your idea to NASA engineers and they say, wow, that's a nifty idea. Instead of just 2, what if I wanted to have 4 baseball sizes in there?
That's a great question.
Now this is not a requirement. I'm just throwing you an early question that you might get. Okay.
So my immediate thought to fit more in there would be just to lengthen the tube. I'm not exactly sure on the distance right now for fitting 2 baseballs plus space for padding is off the top of my head, but you could more easily expand the tube out in length and just like make it longer if you wanted to fit more in one container. And then if you do like 4, then you would have to have removable. You would have to have 2 at least removable, so you can get the 2 innermost and then the 2 outer ones. But
Okay.
that would be my first.
Two next to each other.
Next to each other?
Yeah, or you could make it like a oval, and then
Sure.
handle
Okay.
this way.
And don't struggle with that. Right now, I want you to think about 2 baseballs. Okay. Now, are you going to have a latch between the the 2 pieces that come out?
Oh, if we were to do 4?
No.
No.
Stay with what you've got.
Oh, you mean like the 2 ends?
Yeah. So is there any kind of latching mechanism for either side, either or both sides?
Since we were using PVC screw caps, the caps would just screw on to each other.
Oh, okay.
But if we were to do something more cardboardy, like where we just like slide the ends on and off, we would probably have to incorporate a latching and a bunch of gaskets and stuff.
No. You're thinking of screw ends, and I think that that's smart. So, if you've got it screwed on, stick with that because I think that's fine. In terms of PVC, I think you're going to end up with some really big pieces. So just be aware of that. But continue to explore because I think you got some nifty ideas. Okay.
So one thing I would suggest is maybe on your caps to have a window or some way for the astronaut to see into this tube to know what if it's full or if it's half full or if it's empty. Some indication of because it's all enclosed right now, and it's always good to know if something is full or not full, half full, whatever.
That's interesting. I hadn't thought of that. That's not a bad suggestion, Flo. I like that.
Yeah, just it's something that I notice on cooking, right? If I have oil and it's in a colored container, I can't tell, but a lot of my containers have some kind of window actually on the side, not on the caps, that I know what's in there, how much.
Huh. I kind of like that idea. That's good thinking, Flo.
Thanks. What do you guys think about that?
It is a good idea for like if we have 2 sides open, obviously, but if we had one side, wouldn't you be able to see into the full tube or not?
Huh.
Before you open it, you need to know.
Before you want to open
Yeah.
it? Oh.
Yeah, before you open it.
At all, do you know if there's something in here?
Right. You need to know before you
the
even
light's
open
lighter,
it.
so you wouldn't know as well.
That's true.
So you need some indication. My only concern with a window is just more you have mixed materials next to each other, and then you got to come up with some way to seal it and stuff. But
sure,
you
other
know,
than that,
you could do more sophisticated, though. I wouldn't myself if I was up there. I wouldn't trust it, but you could do some kind of electrical system too that tells you, or even a scale, something besides windows.
what if you do like on commercial products? They have like on a deck of cards, they have a little sticker that seals the thing closed, and then you rip the sticker to open it. So then you can just look and see that the sticker's been ripped, that it's been opened.
Yeah, that's good to know. Yeah, that's good to know also. But it could be half full and the sticker would be open. And you would not know it's half full. You would think it's full since the sticker was open.
That's true.
Good thinking. Just some kind of visual representation that you've used that box or that side of the box.
Or you could actually even write the number of the rock on the side of the thing and know that it's something in there, right? Somehow to know what's in there or what's not in there.
Okay. Good thinking. All right. Any other thoughts, team?
I have a question.
Yeah, go ahead.
So when it comes to testing this, our like main goal is to create a container that it doesn't contaminate, but like testing how if it would get contaminated, like how would you do that?
Good question.
Okay. Good question. A large portion of the people are going to be doing some kind of a 3D print. And so because that's layering, it's probably not going to be sealed. Does that make sense?
Yeah.
Now, but if you use PVC pipe to check to see if it seals or not, you could probably take it all the way down to the bottom of the pool and be able to see how that works,
To
right?
see if water like gets into it.
Yeah. So if water gets into it, then it's probably a good indication that air would get into it as well. Is that okay?
Yes.
Yeah, take it, put it in a tub even. You don't have to have a pool.
Yeah.
The
Well-
pool is better because of the pressure. But
Right. If you can put it in water, that's okay. That's a good sign. But if you take it to the bottom of the pool, you'll have more of a pressure difference. And it's been a while since I've been scuba diving, but I think it's something like 30 feet is 1 atmosphere. Does that sound right?
I don't know.
Yes,
I
it
can't
is.
remember.
Mr. Mansky says yes.
There you go. Okay.
Every
I'll
30
trust
feet is about 1 atmosphere.
There you go.
There you go.
Of course you can know
Any other question?
that.
Questions? No? Okay. I think we're good then.
Yep.
Yeah,
Excellent.
good job.
Good job,
nice,
team.
Nice design. So thank you for working on that, and you have a wonderful afternoon there. Now is it?
Thank you.
Now is it the end of school?
No, we're in our last hour.
Oh my goodness.
That's right. I think we like this style where it's done in school instead of after.
Yeah. Last team, right? One more
Okay.
team.
Our last one. These are the jumping robots.
Oh, excellent. Okay.
Is it in the physics room?
Yeah.
I'm a slide there. Never mind.
Sure.
We'll be able to see it. You want to?
Yeah, you'll be fine.
Okay, I mean, I have all of my data. Jack, do you want me to move over? I'll just, you want to move over?
Yeah, that's good. So we can see all of you.
We've got
So
a pretty good sized team too.
Yeah, yeah. Well, we need that for the jumping robot, actually.
Oh, what is that?
You see that one?
It's coming. There it is. We see
There
it.
it is.
Team Polaris. Meet Waldo.
Sure, Austin.
There we go. Thank you. All right. So we are Waldo, Polaris, but
Yeah, there you go.
we're making Waldo. So just quick reintroductions. I'm Austin Ledeen.
Asher, Burley.
I'm Jack Brenner.
I'm Lyle Scanlon.
I'm Hunter.
Carlson.
Yeah.
Excellent.
So kind of another refresher we told you last time, but there's a lot of like architectures you could try and kind of choose, and we did kind of go with a model pedal design similar to Salto. We did look at a lot of other options to try and find what was the best, but we chose Salto because it's just the versatility that we could do with it. Or this is Salto-like design.
Yeah.
So here are some of the CAD drawings we worked on. This is what we showed you last time, and then this is version 2, what we're showing you now.
From version 1 to version 2, we did some force testing on version 1, and we added 4-point linkage, and we extended, you probably can't see it, but this arm to add torque.
Okay.
So in our first iteration of this leg,
we had a measurement of 3 centimeters in between these two. And just by like increasing it to 6, we halved the initial joules it takes just to get enough torque to jump.
Okay.
And also we did some weight savings, so you have some cutouts. These are hollow, other than for the mounting parts. So now our target weight is about 640 grams, as opposed to the kilogram that we were talking about last time.
Okay, very good.
All right, so we also figured out how we're going to mount all of our parts together. We're going to use like a seating method. So in FRC, we do this with larger parts that are under a lot of force. These rails right here will be carbon fiber in our CDR model, but they'll be seated in little recesses that we designed in here. You can kind of see them. These are printed out of PETG. And then they have UV cured resin that goes down the side, so they're like airtight and sealed. There should be no movement.
Okay.
And then this is like a center pivot shaft. Eventually that'll be free spinning bearings, just so that this whole part can spin on its own. That's your
okay.
So if you can kind of see what I'm holding, this is like the version 2, although this one has a little bit snapped off. It should be about this long. But
hold on a second. Let me see that better. Okay, so this is your version. This is a little bit later version. Okay. Show me how this is going to jump. How's this mechanism work?
The top kind of main like hub area with all the components would be up above here. And then the actual like foot or ground would be like down here.
So
and
this
then
is a herringbone gear mechanism. These two spin completely independently from each other. So the lighting's terrible. So we've got one pinion on the top here, and the other one is mounted on the bottom to a separate gear. You can kind of see it. Yeah, that'd be nice.
And so,
although the lighting's
there you go. Okay.
Yep. So in the final jump sequence, if you can imagine, this is significantly longer. It's in its compressed state. Eventually, we'll have this be flexible, so it can do a supercharge, sort of like a natural spring, and then this will pivot downwards. And
gotcha.
Then this whole thing
so
pivots.
So you guys are mimicking the a cricket leg, is that correct?
Yes, we took some inspiration from animals. Also, Salto 1P was a saltatorial locomotion device.
Yes, I remember that one.
It's got its own like natural spring.
Very good.
Yeah.
Okay, so where are you going to be placing your springs?
So our springs will likely be stored in the body of the main robot above this.
Okay.
Unless we can find something that efficiently goes in between your top pivot and this like is our B link or our ground link in the forward linkage. So we need to put tension in between this and this whole body.
Okay.
The only issue we've had with that so far is when you're winding it up or like charging the energy, that has a much greater force capacity than it would be if we had like a separate spring up in the body of the actual robot.
So what kind of springs are you wanting to use?
So we were thinking about using a rotational spring, so like a little piece of rubber. If we're doing it in the body, so it'll like pull against a fixed piece of rubber. That way it's like already stored. That's sort of what Salto does, except they have a metal spring as well in their leg. But if we were to do like the saltatorial based on like animal muscles, it would just be like a metal spring or a rubber band of sorts.
Okay. All right. So I don't know. Can you guys see me okay?
Yeah.
Okay. So for example, on a rat trap, you've got torsional springs, right? I don't know if that would work for what you were trying to do. Okay.
Yeah.
And then I went over to the hardware store and I picked up a tension spring like this, right? And that might work for your other option. Is that correct?
That is correct, yeah.
Okay. And so part of my suggestion is if you guys have you guys already looked at your springs that you want or not?
We've done some testing, but we're not completely certain on where it'll be located yet because we don't have our spacing and our designs finalized. So that would kind of necessitate it. I've got some other questions that could also like dictate where our spring is going to go.
Okay.
So your torsional spring with like the mouse trap, we were thinking about that, except currently our pivot has too much bulk to fit another spring inside, and there's 2 separate pivoting parts. So,
Okay.
yeah, go ahead.
One thought for you is, so there's another type of spring, right? Kind of like what they might use in a watch, right? Or
Yeah.
or in a tape measure.
Yep.
Does that make sense?
Yeah.
And that might help you with what you're doing there.
Indeed.
Okay.
Mhm.
Now, so some of those, if you go into the hardware store and say you're looking for springs, they'll send you over to this bin and it'll have like 20 drawers and each one of them has like 20 different springs in it. Check that out just because you can do like this.
Yep.
I don't know that they'll have as many different springs as what we're talking about, but they will get you on a good start. Is that okay?
Mhm. Yeah.
Good
We
job.
do have
Keep going.
capabilities to manufacture them too. And then my other question for you, we are currently using herringbone gears, which are like the V shape if you're familiar with them.
Yep.
They've got great force dispersion, so like good contact, but we were wondering if we should switch to belt drive. That way, instead of the force being on just one contact point, it's wrapped around the outside of the circumference. It would also like alleviate a couple like points of contact, and then we could potentially go like away from using a planetary gearbox for our gear reduction.
That's interesting.
Let's move on.
So one of the advantages you get out of the herringbone is potentially are you minimizing some of your mass, right?
Yeah.
And so because if I'm adding a belt, could I be adding some extra weight to it? I don't know. I think what I would do is probably choose one and go with it for a little while, and then if you start having problems, go back to the other one.
Yeah.
Sorry, I wish I had a better answer for you. I think that's something that you'll have to kind of mess with for a little bit.
Mhm. And think about durability, because my sewing machine is 50 years old and still has that belt on it working.
Yeah.
That was the other thing. So with like a constant rotating herringbone gear, you've got a lot more contact points that are happening and engaging. So if any lunar or foreign material gets in there, that could throw it off. Another advantage to the belt drive is you've got a significantly larger surface area of contact.
Mhm.
So if one tooth gets off or if it skips, there's still other ways to catch it. Whereas with
Yeah.
you kind of be off or misaligned.
You mentioned dust in the belt. I don't know that that's all that big of a deal because it seems like it would come out fairly easily.
Yeah.
So I don't know. It's worth thinking on. I like your thought process. Good job, team.
That was another point of discussion. So the main body of our robot, currently we just have it as like an outline because we haven't placed all of our components to where where they will finally rest. But we could use procedurally generated like 3D designs to enclose them all. Would you recommend that they're sealed from the outside completely or breathable and accessible like without a panel or anything?
Anything you can do to seal it is a good idea. But of course, part of your difficulty is weight.
Yeah.
So if you can keep it sealed without putting a lot of extra material on there, I think I'd do it. That's
Sure.
good thinking.
Mm-hmm. And we can do lightening on the inside and just have like a silicone or a nylon seal.
Sure.
But in actuality, I remember the robots from last year, and the kids kept having to go replace parts. The battery would be dead, something would break. So you should always bring extra parts and be able to replace them.
Yes, ours broke.
Yeah, it was happening to everyone. So.
Zach, want to talk about machine learning?
Yep. And back on the programming side with machine learning, we do see a potential use for having AI in our robot, especially with so looking at reaction wheels a bit. So having some sort of way to help adapt it, like if we're iterating over multiple designs, we don't have to manually retune a mechanism every single time, and it's taking like 10-20 minutes to do so. That would be helpful like for time saving. But even so, we could just
still might regardless have like a heuristic way of doing it with like a PID controller and use like a couple of jumps as training data for that. There's many ways, TensorFlow, PyTorch, those are just built-in Python libraries that are fairly easy to use. But yeah, definitely we should at least start off with a heuristic, just a good enough solution, try and keep it from not completely tipping over before we try and go for a fancy solution.
Indeed.
Okay. Well, and I'm not opposed to that, but I would be worried about trying to fit. I mean, any kind of machine learning is going to take a pretty significant amount of computing power, as opposed to trying to keep it lightweight. And I'm thinking about battery power and things like that. But if you have a good way to put in some AI and do some machine learning, I'm not opposed to it. I think that's a good idea. Just be aware of, those extra power constraints may cause some difficulties.
Yeah, we could even do something just not even while it's running. We could just have a PID controller, and after every jump, it could be like, hey, let's use this data. Let's like rate it if it's good or bad compared to my previous launches, and then slightly adjust it afterward. That could be a less intensive solution than doing it dynamically while you're running.
Good thinking. I think that'd be a great way to minimize that power draw. Good thinking.
Yeah, I like the use of AI in something like this.
Okay.
If you're smart enough to use it, that's great.
And then just a little bit about the actual hardware. We run just two different types of boards, just kind of like a slave and a master, pretty much. The TNC, the one up top, we're going to be running C++ on that thing. It's going to have all the sensors and motors directly attached to it. Just trying to keep it fast and performance. Trying to just have all the main performance on there, just so there's a low latency in that. Just when we're grabbing encoder data, trying to figure out where the gyro is, going to try and spin a wheel, like a reaction wheel really fast, trying to adapt it. And then we can have on the Raspberry Pi just the overarching, just some Python connections. If facilitates our Wi-Fi / Bluetooth, the connections with actual astronauts. But it can just say, hey, TNC, just jump, go and do that. You just balance yourself, come back down, let me know when you're done. And just tell me when to take a picture. And the Raspberry Pi would have the cameras attached to it. That would be a lot easier to do in Python on a Raspberry Pi rather than doing it all in C++. Just trying to save ourselves some time and effort. And trying to run something like Linux, like a small scale like Flask, trying to keep it very light, not trying to keep it performance, the whole thing, trying to redundant, performing well and simple.
And that sounds good. What do you already have a camera chosen to go along with that Pi Zero?
So we've got a couple cameras depending on like how big our server and our processing unit actually is. So we've got a lighter camera that would be lower quality, but if we've got like a lot of AI or like a heavy Flask system, we would use like less bit processing with a lighter camera. But if we do end up making like a super light like operating system for this whole thing, we could use a higher quality camera on there. Higher quality also takes longer time to process and then more power draw. So
now what about the transmission? Are you thinking Wi-Fi or Bluetooth, or what do you want?
Eventually we'd like both as an option. So it would host its own Flask server. That way it would just be like a remote serial port connection. You could just connect to it with any device at any time, as long as it's in its like serial mode. But if it failed or something, we would have an I2C connection, which would be physical. So in a dock that we're designing, you would just have a USB port. That way, if something goes wrong and it does not have its server anymore, you can just back up what's already on it.
Sounds good. Excellent.
Actual communication between the two boards that I talked about.
Yeah, so the communication between the two boards will likely be serial. That way they can send a constant stream of data in between each other. The TNC 4.1 will be in charge of all of our accelerometers and telemetry data processing. So it will just send data back to the Raspberry Pi. The Pi does draw more power, so we'd like to have it in a sleep mode while the jump is actually going. So once it sends the jump command, the TC will take over. And then it's sort of just like a dynamic pair between the two of them. Yep.
Very good.
All right.
All right. Do you have more slides?
Yep.
Here we go.
So for our material choice, for strength, like in the legs, we went with carbon fiber. It's because it's lightweight and strong. Carbon fiber is also stiff, so it would ensure that we have precise movements, like during jumps and repeated jumps and landings. And then the aluminum is there because it's low weight and it's strong. And how the reaction wheels, I can't speak today, sorry. The reaction wheels will spin more or spin efficiently without adding unnecessary mass. And it also handles the heat generated by the spinning parts well, and it's durable enough to withstand the forces involved in stabilizing the robot before landing.
Okay. So, oh, never mind. Keep going.
You talk.
Well, I was going to ask, so I see you've got tubing there, and I remember there being some tubing on your other stuff. Do you have a plan for specific parts or anything that are going to be out of aluminum or carbon fiber?
So in our actual design, I'll come up by you again. These are PETG parts, like I said, but we've got our stock material already, so we've been testing with forces on them. All of the pins where they pivot will likely be aluminum, and we do have access to some machines. So if we have like high what would that be? High force components, we can machine them out of aluminum. And then all of our rails will be carbon fiber. So this is like a slightly more flexible material. You can kind of see that. It's a natural spring. And then these two are the tubes. So like super rigid, super precise.
Okay, very good. Thank you.
So just as our main drive motors, we're going to be using BLDC motors, brushless direct current motors. Just because like they've got higher power and torque, higher heat dispersion, and less friction. We haven't decided on our actual kilowatt, like hours for the battery, not for the battery, for the motors. But for our reaction wheels, they'll be lighter, high acceleration and high speed, but they don't have to have like a lot of turning power because they're just constantly spinning with PIDs. And then our main drive motor will likely be an outer driven, sort of like the black T motor you can see on the side of your screen. This guy. So it's got a higher circumference, that way we can mount it to the outside of it and get the most contact area with whatever we're driving it with. And then depending on if we go with belt drive or a planetary gearbox system, that could actually be mounted inside of it to keep it out of harm's way and like tighten the robot even more.
Right.
They're smaller, more torque.
Okay.
Yeah.
Okay. So right now I see that you've got one leg in prototype. Do you have you been working on some of these other parts?
So we most of our other parts are stock materials currently, and then the rest of the housing wraps around our components. So we need to figure out like where our actual components will be placed before we build the real robot housing, because that'll be super tight to them. And then we've just been experimenting with leg designs because the component, like the housing, is based on where the leg goes.
Okay, very good.
Our current design is to kind of have 4 balancing like stability legs that'll come out of the housing, and they'll be just static, but there to assist with this leg. So it doesn't have to do all the work with the flywheels and everything. So it can just kind of land and get to a spot where all of those are connecting. So if it's done and actually needs to hold it, or if it needs to almost say recharge a jump, it can be able to do that without having to work on all the balancing stuff.
Okay. Interesting. All right. So do you have some kind of a sketch to show me what the overall robot is going to look like?
I mean, this is kind of the total thing. You can kind of see the leg here and where it'll hit the ground, and then where the, say, static legs would be too, with the robot housing.
Okay.
And then kind of visualization of the flywheels and the cameras. We plan to have 2 cameras to be able to see as much as we can.
Okay.
2 flywheels to be able to balance in both directions.
Yeah. Okay. And what kind of weight are we looking at? Any ideas?
Our target weight is 640 grams. Our maximum weight is 830.
Okay.
With 830 grams, the amount of the dominant joules per jump would be about 40, which with the battery and power system we're looking for would give us about 60 jumps on a single charge with camera action as well. 640 would bring that up to 300, so we could go for a much longer time.
Okay. All right.
Trying to be light and under a kilogram.
Sure. Okay. All right. Now help me out, just because you probably said this and I didn't quite catch it. So you've wound up so that you've got your tension stored up. What's the mechanism for how it releases?
So depending on which spring we choose and where we'll put it, the other benefit of having a BLDC motor is you can just back drive it. So it would just be like a little servo release, or just releasing the brake mode function on the motor. The motor will hold it up, it'll hold it in place until the jump signal is sent, and then it'll release brake mode and just backspin.
Okay.
So
well,
and there's no ratchet.
So if not all motors will spin backwards the same without having a lot of friction. So trying to choose the right motor for that could be pretty important. Yeah. Okay. Excellent. Do you guys have any questions for us?
I mean, you've answered them all so far. We've gone through it, but
okay. All right. Any other thoughts or comments you want to make about the project?
I mean, I think we're good. It's going well. We're excited to present you guys.
Okay.
Yeah, I'm impressed with your knowledge of all this stuff. You're doing a great job, and you have a strong team because everybody has a little bit different skills, which is really important. So keep working together.
Why'd you guys choose this project?
We wanted a challenge.
Yeah.
It is a challenge.
This is a tough one. So I can't wait to see how you guys work on this. This is terrific. Good job, guys.
Thank you.
Awesome. You keep up the great work and have a wonderful afternoon. Is your teacher still there?
Yep. Different teacher is here. Hi. If you could. Sorry. Hi. I just
how are you doing?
Sorry. Mansky had to go teach a class, but I have prep. I'm Andrea. I've seen you guys a couple of times.
I've seen you before.
Yeah.
Good to see you again, Andrea.
Yeah. So I only got to see the last 2 conversations because I was teaching and now he's teaching.
Ah, okay.
Seems like everything's going well. Do you have any comments or questions or concerns for the advisors?
No, I think things are going pretty good. So I look forward to being able to see you later on.
Yeah. I'm excited.
And Nancy and Cody are your mentors, so I'll make sure they get to see this video.
Great. Well, thank you.
Okay. Thanks
awesome.
a lot.
Thank you. Thank you, Glenn, so much.
We appreciate your expertise. Have a great day.
Thank
Excellent.
you.
See you soon.
Have a great afternoon. Glenn, thanks a million. I can't